So, good morning, everybody. Good morning. I see some students, I think they are still waking up. But let's start our session for this last day. So our session will start with Professor Zanotto, which will tell us some things about crystallization in glass. So, Edgar, please. São 50 minutos.
Você me avisa depois de 30, depois de 40? Tá. Você me dá toque. Good morning. There's only a few people here, but the good people are here. That's the important thing. Quality is most important, not quantity. Thank you very much for coming. I know you are all tired. You have been working last night, I heard, a lot. So I fully understand this. I hope some of you, in addition to learning about glass science, became interested in capoeira fighting also. And later on, we are going to send videos of all of you, playing a little bit capoeira in São Carlos, working very hard every evening. I know, I have been following you. But let's talk about glass crystallization. If you are really interested in this topic, I recommend that you take a look in this review article that we published recently. It's very comprehensive, where we describe all the developments that have been going on in the past 2 decades on understanding crystal nucleation in glasses. Well, just a brief introduction. If you look at George Morey's book, published in 1938, he says that uncontrolled crystallization is one of the main problems in making glasses. If you want to produce a glass, to make a glass, the key thing is to avoid crystallization or devitrification. Devitrification is used to describe uncontrolled crystallization, devitrification. It's a problem. And then, of course, you can control crystallization and produce extremely nice microstructures, which, in addition to being nice, they control all the properties of the resulting glass ceramics. And glass ceramics, of course, it's a derived family of extremely important materials which have unique combinations of properties. And the most important feature of glass ceramics is combination of properties. Combination of properties. For instance, you can combine bioactivity with higher toughness than glasses, or optical transparency with toughness, or very low thermal expansion coefficient with high thermal and chemical stability. So combination of properties. This combination of properties is achieved by microstructural design. Microstructural design is the key feature of materials engineering. You can control by changing the chemical composition and the thermal treatment, the grain size distribution, the shape of the crystals, the texture, porosity, the percentage of crystallinity, the type and number of crystal phases, and also the properties of the residual glass. All glass ceramics have a residual glass left. So all of these features determine the properties of the glass ceramics. So through the glass ceramic route, it's not very easy, but possible to control all these features. Okay. Then somewhat surprising finding, if you look at the keywords regarding to glass science and technology published since 1950, the most frequent keyword in glass science is crystallization, even more than glass transition. And if you sum up crystallization with crystal nucleation, crystal growth, and glass forming ability, then by far, these are the most important keywords on glass science because of the two facts that I just explained to you. You either have to avoid crystallization or you have to control it to produce glass ceramics. Anyway, there's a nice article published by the Royal Society of Chemistry in the UK. Do you really know what glass is? You know, take a look later on in the internet, ask this question, and let's see, and think about this. Do you really know what glass is? I'm not sure if I know. You know, I have been trying to understand glass for a few years now, and still don't know exactly what glass is. But if you look, I'm sure you have seen this. This is the most famous figure in glass science and technology. We have seen this in your previous classes, in textbooks, and here in this conference several times. But I'm going to show you an unknown part of this plot. The known part is that, okay, you have a liquid. You have a liquid above the liquidus temperature. The thermodynamically stable state is the liquid state. And then if you are able to avoid crystallization, have a supercooled liquid, at some stage, the supercooled liquid can no longer relax during your experiment, and then we have a glass. So a glass is just a frozen liquid, temporarily frozen liquid, because as Colin has shown, all glasses relax. All glasses, your eyeglasses are relaxing. Glasses are relaxing all the time. Of course, at room temperature, it will take a very, very long time for relaxation. If you're here at room temperature, it will take a long time. And you can also ask this question in the internet. Do cathedral glasses flow? Is it true that very old cathedral glass windows have flown along the years and they're thicker at the bottom parts? Take a look in the internet. You'll find out the answer for that question, right, Colin? However, the key feature here is that, you know, if you heat up a glass a little bit about the TG, it will crystallize after some time. And also, if you heat a glass here, this is the typical TG of this glass, but if you heat a glass here, say 20, 30 degrees Celsius below the melting point, the glass will relax back to the supercooled liquid state, and you can measure. You can measure these things. People like Colin, his students, and Ricardo, there's people who dedicate a lot of research time trying to understand the relaxation process. And you can measure these things like in a few hours, a week or so. Of course, it becomes, you know, longer and longer and longer and longer. The relaxation time becomes longer and longer. At some stage, we do not have enough patience to measure. But I'd say typically down to 50 degrees Celsius or so, below the TG, you can measure this relaxation process in laboratory time scales by measuring any property, the density, the enthalpy, you know, the CTE, the viscosity. You take any property and measure along the time, it will change. Now, the unknown feature, this is well known. Oh, and then, of course, if you wait longer, the supercooled liquid will crystallize. You all know this, right? But this is not well known. The birth of the first critical crystalline nucleus. If you have a glass at this temperature, and then you wait longer, it will relax back to the supercool liquid state. And then the first critical nucleus will form, and then you have crystal growth, and you have full crystallization. So the time to form the first critical nucleus can be longer than the relaxation time. But if you come here, take a look here at this temperature. It can be shorter than the relaxation time. So there are situations at enough low temperature where the time to form the first crystalline critical nucleus is shorter than the typical alpha relaxation time. And this is a feature that not many people are aware of, and no textbooks shows this kind of feature. And the idea here is that from a physics point of view, once the first critical crystalline nucleus is formed, you no longer have a glass. Because crystal growth is a spontaneous process. There is no thermodynamic barrier for crystal growth, just a kinetic barrier. If you form one nucleus, that's it. That nucleus will grow, and then the material will crystallize. So, of course, this is very specialized, but if you are interested in this comparison of, the time it takes to relax with the time it takes to form the first critical nucleus, I refer you to a very nice paper that was authored by Rebecca Welch and Colin and colleagues and Daniel, who is here. I think this is a very nice paper where we tackled the famous Kautzmann paradox, and we demonstrated that there are several routes to escape the famous Kautzmann paradox. One of these routes is that crystallization starts before relaxation at low enough temperatures. So the Kautzmann paradox does not exist. I know this is a long story. We can talk more about this in the coffee break or tonight in the dinner. But take a look. This is a nice paper also that if you are interested in glass science, you should read, I think. Okay. Now, so coming to the Royal Society of Chemistry question, do we really know what glass is? Well, this is my view. There are different views in the internet, in textbooks. My view of the glass is it's a non-equilibrium, of course, non-ergodic material, non-crystalline, that shows somehow a glass transition phenomenon. And some important features of glasses is that their structure of glasses is the same as the structure of their supercooled liquids, of their isochemical supercooled liquids. And also they spontaneously relax towards the supercooled liquid state. Even if you fry any glass to the outer space, it doesn't depend on the gravity. It's a spontaneous process. That's why glasses are unstable. They are non-equilibrium. They are unstable against the supercooled liquid state. And the supercooled liquid is metastable against the crystalline state. And finally, in the end of their lives, depending on the temperature, on the chemical composition, all glasses will eventually reach the thermodynamic equilibrium and crystallize. So this is my view, and John's view, and some other people's views on what glass is. But not everybody agree with this definition, I should say. It's up to you. There are several others in textbooks. Okay, now, since you now are experts in capoeira fighting, and I guess some of you have not seen this video that we produced, that's our view of the glass transition. Eu preciso do som, Maicon. Maicon? ver se tem som. Michael? Ele não está lá. No sound. Lá precisa subir, os caras, essa escadinha aí. Mas acho que ele não está lá. Ele não está aí, Oscar? Não, pode abrir a porta. Som do vídeo. Vai. Tudo bem. Ah, eu não sabia que eu tinha que fazer isso.
Tem que ligar no Só vou ligar, nosso senhor.
Corre lá. Oi? Oi.
Liquid. The structural units, people, move fast and independently. Supercooled liquid. The structural units diffuse cooperatively and slower than in the liquid. Glass. The structural units are disorganized and do not significantly diffuse. They vibrate and start to relax toward the supercooled liquid state. Supercooled liquid. The structural units diffuse more cooperatively and even slower than in Act 2. Crystal nucleation. A critical nucleus forms in the relaxing supercooled liquid. Crystal. The structural units are organized and only vibrate.
Okay. Now you can understand after the capoeira testing at Lamav. So let me review with you a very well-known expression regarding the formation of a critical nucleus. So the W, the work, W for work of formation of a cluster of size R depends on the difference in free energy between the supercooled liquid or the glass and the crystal, the strain energy when you form a solid, crystalline solid in a liquid or in a glass, there's strain energy that should be taken into account. And then you also have an interfacial free energy, the new interface that's formed. Most textbooks also neglect this term here, which is okay if you are working above TG. If you are working in a liquid or supercooled liquid state, relaxation is very fast, so there is no problem. Any strain that will form will relax fast. However, if you are working really in the glassy state, that term cannot be neglected. And many people overlook this part because textbooks normally don't show this strain energy. In any case, if you, the final form predicted by this expression is the black curve here. So if a cluster is smaller than a critical radius, it will dissolve back. If it's larger, it will grow. And then you count as a critical nucleus. So the number of clusters that are larger than the critical nucleus that are formed is the nucleation rate. The number of critical nucleus per unit volume per second. This is the nucleation rate. And this critical nucleus is just the interfacial energy divided by delta G in case this term has been neglected. If you are working in the supercooled liquid state, if you are working in the glassy state, you have also to add the neglected term here. And the work for critical nucleus formation is just the interfacial energy to the third power divided by delta GV to the second power. So these are the main terms of the nucleation rate expression. This is the nucleation process. Professor Rino has shown this before for barium sulfide. You know, clusters form and dissolve until a critical size is reached. Then you have nucleation. So this is a real MD simulation of the process I was talking about. And then, how can you compute the nucleation rate? You just have to quench, melt whatever material you are working with above the melting point for some time. Then you quench it very, very fast with quenching rates of 10 to the power 12, 10 to the power 13 Kelvin per second. So nothing forms in the cooling path. And then wait a little bit, and boom, the first critical nucleus is formed. Then you melt everything again, do another experiment, and boom, another critical nucleus is formed. So you repeat a couple of times, 6, 7, 10 times these experiments, you have the average time for the birth of the first critical nucleus at one particular temperature. And then you change the temperature, you repeat the experiments, you can compute the average time for the birth of the first critical nucleus. And then you calculate, if you are above the TG, the relaxation time is short, you can calculate, compute the nucleation rates. It's just 1 over the volume of your box and the average time of the formation of the first critical nucleus. So that's how you can compute nucleation rates by MD simulations. It will work well if you have a good potential, and Professor Rino has developed a very good potential for barium sulfate and other materials. Anyway, so the classical nucleation expression is just, in a simple form, a diffusion term here and a thermodynamic term. And this thermodynamic term comprises the interfacial energy and delta GV. So it's 3 main parameters that control nucleation rates. The diffusivity, say if you are working with nickel, it's the diffusivity of nickel atoms. And W star is the interfacial energy to the cubic power divided by delta GV to the second power. So you need to know this parameter, and this parameter to calculate nucleation rates, assuming that this model works. Then we come back to the question that has been asked before. Why do we bother to understand, develop, or improve theoretical models? The key thing is to understand phenomena, and even more important, to be able to predict. Measurements of nucleation rates or most other dynamic properties is really time-consuming and difficult. If this theory works, you can just calculate the nucleation rate of any glass which you want to transform into a glass ceramic, for instance. So let's see if this... There are other theories. This is one of the most used by far in the literature. So let's take a look in this theoretical model and see how it works. So the main assumptions here is that we have homogeneous nucleation with equal probability all over the volume space. The driving force is that of a driving force of a macroscopic crystal, despite the fact that these crystalline nuclei are very, very tiny. They have a few angstroms only. And the interfacial energy is independent of size and temperature. These are classical assumptions of this model. And again, the diffusion term is quite easy to know if you have like a pure metal. Now, if you have a silicate glass, like a soda lime silica glass, these diffusion terms, falei 30, mas tem que descontar 5. The diffusion term of a complex silicate glass is normally not well known. So people assume that the viscosity can be used to compute this diffusion term. So these are assumptions that people use. And also, the interfacial energy is unknown. This parameter is unknown. There is no equipment. You cannot measure the interfacial energy. You know, put your glass light and measure. It's unknown. So we know more or less the diffusion term, the delta GV, but don't know the interfacial energy. Still, we can test the theory with one adjustable parameter. So let's go ahead. So you make a glass, you crystallize it, you count the number of crystals, so you compute nucleation rates for several times, several temperatures, and then you come here and have your nucleation rate curve in red, for instance, for particular lithium disilicate in this case. You can also measure the crystal growth rate curve, but we are interested in nucleation rate, the homogeneous nucleation rate, shown here on the left-hand side, nucleation rate. And then, if you want to see, this is a node video provided by a friend of mine from Jena. It's a very fast nucleation rate, and then growth. Your nucleation was very fast. You can see growth of a cordierite glass. So this is the kind of things that you can do in the lab and compute your nucleation growth rate. So, okay, let's then see if this theoretical model works. So several people have measured. These are measurements, you know, nucleation rates versus reduced temperature here. Sodium metasilicate, lithium disilicate with some OH, barium disilicate, that's Ben's favorite material, barium disilicate, and some other materials. The typical range is 10 to the power 9, that's 1 billion crystals per second per unit volume, and up to Fresnoite, 10 to the power 17 crystalline nuclei per second per unit volume. This is the kind of experimental range of nucleation rates. And then when you test OO, if you compare the measured values here with the predictions of the classical theory using one fitting parameter. Remember, we don't know the interfacial energy, so we leave this as a fitting parameter. And the difference is 30 orders of magnitude. Not 30 times, 30 orders of magnitude. The temperature dependence is fairly well described. See, the curves are the same, but the magnitude is huge, the difference. And so maybe there was some mistake, and so let's test some other glass. And this, for all glasses, you know, you see the same kind of huge discrepancy, And this is a funny story that there is a famous professor former professor, Alfred University professor David Pye. When I first shown these results years and years ago, he came to me and said, Edgar, you should consider submitting a report to the Guinness Book of Records. This must be the worst theory ever. It's a true story. So I was thinking about that nice suggestion. At least I can publish something in the Guinness Book of Records. Well, I'll tell you the end of this story in a few minutes. So, see, the discrepancies varied from 30 to 50 orders of magnitude or so. The worst theory ever, with one adjustable parameter, the interfacial energy, because there's no independent way to measure the interfacial energy. So, let's then skip some details, but how can you restore back agreement between theory and the experiments? You can force fit the interfacial energy. So we force fit. You can calculate it for each temperature. What's the value of the interfacial energy to bring agreement? And we did that, and you come up with this nice straight line here, just saying that interfacial energy is not constant. It varies with temperature. And it should vary with temperature. It's a thermodynamic parameter. So, but this is force fitting. There is noise here, a lot of problems here below TG. I'm going to skip all this part, but this is in short, this is because that strain energy term has been neglected by everybody. including ourselves, in the past. So that explains, all the noise below TG. Below TG, we have a glass, not a super cool liquid. So it's more complicated, but can be done. Also, people are not patient enough to wait for the system to reach a steady state. And just because Colin, Ricardo, and other people are here, I can tell you that the alpha, if you take a typical lithium silicate glass, 20 degrees Celsius below TG, the alpha relaxation times as computed by enthalpy or refractive index or anything is like 20 hours. In 20 hours, you can relax back to the super cool liquid state. To reach steady state, it takes 500 hours in the same temperature for the same glass. So this is another type of relaxation, Colin. It takes much, much longer than the typical alpha relaxation time to reach a steady state. But that's a long story, and I do not have time to cover all these finest details here. But the thing is, with a fitted constant sigma and viscosity, you have this huge, huge discrepancy. Huge discrepancy. Then, allowing for the variation of interfacial energy with temperature, you can restore agreement, at least above TG. Right. But still, it doesn't prove anything because this was a fitting procedure. So we still did not know if the theory works, if that theoretical model works. Okay. So there are several explanations, and this is nice about science, When you have a problem, you try all sorts of escapes, and you publish papers, and you try some strategies, and you keep going and learning and learning and learning. But none of the explanations that resulted in papers were good enough to explain the discrepancies, etc., etc. So let me then just show one slide about relaxation and crystallization below TG. So this is the classical lithium disilicate glass, nucleation rates, temperature. See the old data here in green. See in green? By old data, I mean data that several people in the past measure nucleation rates. And these are the data showing the break. See, this is the prediction of the theory, and these are the break below TG. Now we have new data. During the pandemic, you see the blue points here? New data. Agreement is restored. You just have to wait 500 hours, and the nucleation rates go up, and you reach a steady state. Very simple. Very simple. So all the other experiments were incorrect below TG. But it's another long story that it's covered in that review paper. Anyway, let me rush and then go. These are Ricardo's measurements of the same glass at different temperatures, just showing that alpha relaxation times are much, much shorter than these times needed for the system to reach steady state nucleation. Okay, now final part. How about molecular dynamics simulations? So testing CNT, you have seen this video already. We can compute nucleation rates, can compute the times to form the first nucleus. We compute the diffusion coefficients also. That's a nice thing. There's no need to use the viscosity as a proxy for the diffusivity. In molecular dynamics, you can compute directly the diffusion. In this case, for instance, barium sulfide, the diffusion rates of barium, of sulfur, they're very similar. So we just took the average. And then when the system crystallizes, the diffusivity drops tremendously for this particular system. But we have here diffusion date, nucleation rate data, so you can, then we could compare, several papers for nickel, barium sulfide, zinc selenide, and germanium. I'll show you just one of them nickel, because this is the most interesting that we had. Nucleation rate here, temperature, and then brute force molecular dynamics. So the blue circles refer to nucleation rates measured by molecular dynamics. This is metallic nickel. Why we have used metallic nickel, I'm going to show you in a minute. And these are calculations using the classical nucleation theory. Look, the red triangles with parameters derived by molecular dynamics. All the parameters derived by molecular dynamics simulations. Very nice agreement. Extremely nice agreement. But it becomes even better because some people had measured nucleation rates in nickel. Now, that's a metallic nickel. It's not a good glass former. So it has a very high nucleation rate. So some people had measured nucleation rates here. Guess what? Measurements in pink, our calculations here in red. And that's why we pick nickel, because we had data and a good potential for nickel. So after all these years, all these problems, all these trials, the classical nucleation theory works, and we did this for several other systems. And let me show you a final video because you love this. Water is one of the most important substances for our lives. This is at molecular scale crystallization of water. See how beautiful this phenomenon is. And for water, also there's a lot of nucleation. People have measured nucleation rates. See, these are measurements of nucleation rates in water. And our MD simulations are here by Azat Tipev, a former postdoc of ours. Azat has simulated nucleations in water, and the agreement is very nice. Agreement, MD simulations, CNT calculations, and the experimental data. Anyway, to finish up, I'd like to call your attention to Colin's work. This is mostly a paper that Colin, work of Colin years ago, a few years ago, 2020, with barium disilicate. Colin was able to compute, this is the, energy landscape of barium disilicate using a well-known potential produced by Alfonso Pedoni. And then from the energy landscape, Colin and his co-authors, but mostly Colin, were able to calculate nucleation rates. Here for a box of 1,000 atoms, because these computations are very expensive, very slow and expensive. 1,000 atoms was the maximum you could go, right, Colin? But for 1,000 atoms, see the calculated curve in blue and experimental data here from several people. Very nice. And then I like this work. I think it was the first one where people used the energy landscape approach, to calculate nucleation rates. And I just proposed another work last night to Colin. Anyway, to finish up, I think computer simulations techniques have been fundamental in proving the effectiveness of the classical nucleation theory in describing nucleation rates. So the final word, after 50 years or so, many people involved, this theory works. This theoretical model is really good. And with that, I think I stop here. Thank you very much.
Okay, thank you, Edgar, for this nice talk. Short overview about crystallization and nucleation with some results in molecular dynamics. So the session is open for questions. Isso aqui.
Thank you, Professor. Is there a good way to calculate the surface energy in MD? No.
Okay, due to the limited time, I did not explain this, and thank you for your question. How will we do it? You insert an artificial crystalline nucleus in the liquid, in the supercool liquid. You create a crystalline nucleus, and then wait a little bit. If that nucleus dissolves, it's because it's below the critical size. If it grows, it's above the critical size. So you play games with the size of this seed, crystalline seed, and you find the critical nucleus size for different temperatures. If you have the critical nucleus size, it's easy to calculate the interfacial energy, because the critical nucleus size is just the interfacial energy divided by delta G. If you know delta G in the critical nucleus size, you know the interfacial energy. So that's the clever way to get the interfacial energy
And
from MD.
Okay.
Yeah.
Okay. I have another question. Is there difference for calculation saying nuclear rates for using the data from using the viscosity data from experiments and the simulation data from diffusion coefficients?
Good question. Good question. Yes, if you calculate nucleation rates using viscosity, you get incorrect values of the nucleation rates. We also found, but I did not show here, that if you don't have actual diffusion data, you can use crystal growth rates. If you measure crystal growth rates, you can compute back the diffusivity controlling crystal growth and insert that diffusivity in the nucleation rate equation. So that's the best proxy. The best proxy is the diffusivity derived from crystal growth rate data.
So, in my opinion, the diffusion coefficient is more directly we for calculation the nuclear rate. You use the diffusion coefficient is more directly.
If you have direct measurements.
Oh.
No, that's the best scenario. If you have direct measurements, but you know, if you have a complex silicate glass, there is hardly, direct measurements of diffusion coefficient. But that's the best scenario, of course.
Okay, thanks, Professor. I have a question about glass moisturing. How glass moisturing can change the crystallization, the temperature of crystallization?
I did not understand.
When you have some water on your glass network, it could be changed the temperature, the temperature of crystallization.
Yes,
Yeah,
yes.
and-
OH, dissolved water, has a huge, huge effect. I think I have shown one slide here very quickly, glass with a higher content of water. Let me try to find out here. See, this is lithium disilicate, and this here is lithium disilicate with maybe 500 ppm of OH. This has maybe only 30, 40 ppm of OH. All glasses, most glasses have a little bit of water dissolved. And this is on purpose with 500 ppm of OH. You see, you have an increase of one order of magnitude nucleation rate. And the maximum also shift to lower temperatures. So yes, water has a very strong effect on nucleation, also on growth rates. It increases nucleation growth rates.
Thank you for the nice talk, Professor. So there was an equation which talked about the work to find the critical nuclei. So in that equation, you have the term strain energy. So I wanted to understand in a little bit more about the physical meaning of the strain energy, because what I understand in terms of like liquid electrolytes, the strain energy of a mobile sodium ion is to come out of the tetrahedra. So the strain it faces, the mobile ion, that is the strain energy in that terms. But in terms of crystallization, could you please explain a little bit what is the strain energy?
Yeah. This strain energy is because, say, you have a supercooled liquid, and the molecules are all comfortable in their positions in the supercooled liquid. Suddenly, a solid forms in the supercooled liquid. And this solid 99.999% of the times has a different density than the liquid. So you have strain. The solid can be either less dense or more. Normally it's more dense, but you have strain energy because the atoms have to accommodate themselves for that foreign particle that is forming. So you have a strain energy. And this strain energy can be calculated and taking into account if you are doing experiments below the TG. It's a little bit complicated, but it can be done, and I can send you papers on how to do that.
It's not the same thing as the, it's not the same thing.
Is it?
Yeah.
Is it?
Yeah. From
Thank you for your nice talk, Edgar. Below TG, when the glass relaxes towards the supercooled liquid, the relaxation does just involve, let's say, changing rearrangement of the tetrahedra. You don't have a bond, like changing coordination or changing bond breaking, yes? Or what kind is structurally? What is the kind of relaxation, alpha relaxation is related to this relaxation?
Yeah, very good question. He is asking what happens to the glass structure when it relaxes back to the supercooled liquid state. Ricardo has done some work, and also Henrik, who is not here today with Helmut, have done some NMR work. So for, let's say the lithium disilicate, our Drosophila of glass crystallization. For lithium disilicate, Henrik has done very sophisticated NMR experiments showing that the lithium atoms, and they are the faster moving species in lithium disilicate, the lithium atoms rearrange first. They become their environment, coordination number and distance, closer to the crystalline state. So when you relax a lithium disilicate glass, but that's true for a sodium disilicate or a potassium disilicate, the faster moving species rearrange first. They become closer and closer and closer to the crystalline state. And then you have a change in the QN unities. They also change a little bit, and I can refer you to a paper published by Ricardo and Sabiasashi-sen, showing that also the QN unities also become more Q3 in this case. The crystalline state of lithium disilicate is all Q3. So the glass has like 70% Q3. When it relaxes, it goes to 72 or 73% Q3. It becomes more crystal-like. So the glass structure becomes more and more crystalline-like. In the end, they will crystallize. But the structure approaches more and more the crystalline state. You know, that's what we have measured for lithium disilicate at least. Also, there's molecular dynamics work by Morten in Denmark, I think, for a sodium silicate system, showing that even the ring distribution, you know, the SiO2 ring distribution also changes during relaxation.
You have a change in coordination number also?
Well, in a plot, you think that these changes are large, but they're small, like 1%. The density changes 1, 2, 3%. These are small changes. That's why it's difficult to measure relaxation. You have to use techniques like refractive index, which is very sensitive to structural changes, is one of the best, or enthalpy. But it's small changes in structure.
Okay.
Great talk. Thank you, Edgar. I was wondering what you thought the origin of this anomalous relaxation in the nucleation is due to, since it's not taking at the same rate as alpha relaxation or any of the other processes we know that are going on. So what do you think is causing that delay?
Yeah, well, you know, the alpha, as I said, alpha, and we all know that alpha relaxation involves a minor structural change. If you measure density, for instance, we have plots here for density. If you are 20, 30 degrees Celsius below TG, the density will change by maybe 1%, even less. So it's a really small change. For crystal nucleation, it's a huge, huge change. I mean, you have to completely rearrange, you know, the glass structure to form a crystalline nucleus. So that's why it's so long. I mean, that's qualitatively speaking. That's why it takes much longer. It's a drastic change in the structure, going from the supercooled liquid or from a gas to a crystal. It was a surprise, though. Like, we have this particular measurement at 20 degrees Celsius below the TG that Ricardo measured with different techniques, the alpha relaxation, in 15 or 20 hours or so to almost fully relax, and 500 hours to reach a steady state. But that's the explanation. Small structural change versus huge structural change.
Okay. Any other?
Good morning, teacher. My question is how the molecular dynamics can explain these families of glass that need these.
Habla em espanhol.
Ok. Aqueles agentes nucleantes tem uma família de vidros que só podem cristalizar com os agentes nucleantes. Sem eles não conseguem cristalizar. Então, como a dinâmica molecular pode explicar isso aí?
Oh, this is a very, very good question. He is asking, you know, certain glasses, or most glasses, I should say, do not crystallize in the volume. If you take any glass like window glass in a furnace, it will crystallize from the surface, from defects or impurities on the surface. To induce internal crystallization for many glasses or commercial glass ceramics, you have to add some nucleating agents, zirconia, chromia, P2O5, titania, something has to be included there. So, first thing, I don't think, at least I don't know how to predict the effect of nucleating agents beforehand. You know, what people do, at least what we do and my colleagues do, is try different potential nucleating agents to induce internal nucleation in a certain glass. I don't know if any possibility of predicting. And these nucleating agents they add either by, like zirconia. Zirconia is barely soluble in glasses, so you add 1%, it's soluble, 2%, 3%, and then it's supersaturated, almost ready to precipitate. When you hit the glass, you have zirconia crystals precipitating out, and then they act as sites for heterogeneous nucleation of the crystal phase you are interested. P2O5, for instance, is a very good nucleating agent for lithium silicate glass ceramics. It induces liquid phase separation, liquid-liquid phase separation. So one of the phases become much more similar to the lithium disilicate crystal phase than the other phases, and then you have this effect. So every nucleating agent has a different mechanism, but it's an open question. Colin was asking me last night, what are the open questions? There are several open questions in glass science and technology. I think one of them is predicting the ability of certain nucleating agents to induce internal nucleation. This is open. I don't have any answer for that. But thank you for your question.
Yes. Yes, quick question because we must move to the next.
Edgar, albite is a glass that never crystallizes, yes?
Albite.
Albite, yes. Can these models tell us why it doesn't?
Well, we have published a paper with Daniel Kazar years ago on the extreme glass stability of albite glass and B2O3 glass. B2O3 is another example. So according to some calculations that we did with Daniel, using the classical nucleation theory and several assumptions, the nucleation rate curve of albite is well below TG. So you have TG, the nucleation rate curve is like 100 degrees Celsius below TG. So it should nucleate, but you have to wait a real long time, which is not practical in laboratory time scales. But as I said, it has a lot of assumptions. In these calculations, there are assumptions, but we found that for both B2O3 and for albite, that the nucleation rate curves are really well below TG. So that explains why you cannot observe anything in laboratory time scales.
Okay, thank you, Edgar.
Thank you. Thank you very much.
We must move. So let's move to the next speaker. So next speaker is Eduardo Bellini. He's professor here at USP. So you will visit his lab tomorrow morning, yes, I think so. And Eduardo Bellini will talk about something about sintering of glass powder. So Eduardo is a old colleague, old I mean he is working with us since 30 years, Eduardo, 20, yeah. He did the graduation, etc., all in Lamav. Okay.
Thank you, Anna, for your kind words. Thank you, everybody, for being here this morning after the student night out. I don't know what happened yesterday, but I guess you had some fun. And we'll talk about glass sintering, and that was my life since I was a baby in Lamav. I started working with this. And let's hope everything goes well now. Well, normally we look for glass ceramics that are crystallizing in the bulk, in the volume. And in this case, many times we look for small, very small crystals, submicron crystals that could give some nice properties. And what is very attractive in this kind of material is that you can control the crystalline, the crystal size, the crystalline fraction, and you can produce material without pores in many cases. And in this case, it's funny because always you have this, the format always change here in this system. Well, in this case, we have to put all the materials together, the raw materials, melt, and very often we have to include nucleation agents, and then after melting, we form this into a mold or as a plate or blowing or so. And then you have to give a heat treatment for crystallization, and then you have a glass ceramic. More or less, this is what's happening. You have nuclei in the bulk, and then around this nuclei, you have crystal growth. They meet each other. They hit to each other. And more or less, the structure you have is like this. After acid etching, we see the crystals individually. The glass matrix here was removed, and this is a nice microstructure. Well, going, and these are some examples of glass ceramics obtained by bulk crystallization. There are some advantages. You can deal with complex compositions, and you can design those compositions to obtain what you want, more or less crystallization, control viscosity, control a lot of things, kind of phases you want to have in the bulk. You can use all the sort of machine learning and other things to prospect new compositions and so on. And you can use the forming of glasses in a very high rate. You can produce massive amount of products using this kind of process, control the microstructure, and get a microstructure free of pores. Disadvantages: forming is limited to suitable glass forming compositions. You have to have the viscosity controlled into a precise range. And then it's expensive to have this high temperature form. You have to form in heated molds and everything in high temperature, and that's quite expensive. And very often you need to find nucleation agents, and that's not so easy to find for all the compositions. We know nucleation agents for some compositions that are very classical, but sometimes you have new glass, and then you have a hard time to look for other nucleation agents that could work there. Then we have the alternative to use glass sintering. Glass sintering, we use the powder technology to produce the glass ceramic. We, again, start melting the raw materials, but now we quench it into a frit, pouring, for example, in water, and that's quite easy. You don't have to have difficult forming process in high temperature. Then we have to mill. Everything disappeared here. I don't know why. We have to mill, get a powder, control the size and the particle size range and so on, and use classical ceramic procedures to form now the product. And then you have to heat treat it for sinter crystallization, then you have a glass ceramic. Seems easy. But then what's sintering? We're talking about sintering, and everybody knows what is sintering. What's sintering? Some guess. It takes some powder, compact, and then put in a furnace, and then you have a sintered material. But what is happening inside? Sintering is the transformation of the compact of particles in a monolith. That's driven by reducing the surface energy. It's general, regardless of whether the particle is crystalline, a supercooled liquid, it's a liquid. Here is an example of water sintering. Two water drops sintering. You just have to touch that, and then everything happens very fast. In the case of water, the viscosity is very low. But in the case of a supercooled liquid, the viscosity can be very, very high, and the kinetics of sintering can be very slow. What's happening here is that after the contact, you have the substitution of more energetic surfaces with the environment here, with an interface between those particles. The formation of a neck, and this very small and negative compared to this curvature radius causes a pressure, and material is pulled or transported in the direction of the neck to reduce this curvature radius and coalesce the particles, okay? Sintering is not densification. We used to confound sintering and densification. Densification can happen together with sintering or not. For example, here, there are two crystalline materials. This is alumina. Alumina you can sinter up to full density. But when the materials is transported to the neck region by the surface, only by the surface and not from the bulk, you does not densify. Here is an example of silicon. The white or glitter fraction of this image is the solid material, and in black here you have the pores. This is an example of a sintered material that does not densify it. Did not densify, okay? Well, this is another example trying to convince you that model is nice. Why do we have this is the question that will survive after the school. Raquel made it, asked it, why do we need a model? Well, here we have the example of two water spheres in the state of an ice, so it's solid, just solid ice sphere. spheres that are in contact, and after some time, you see sintering is happening. Again, the material is transported to the neck region, in this case, by sublimation and condensation. And why do we know that? Because we are calculating using different models, and we see here, at least in the beginning of the process, the sublimation and condensation explain well what's happening here. And you can see more or less here that the particle center are not approaching, and the approximation of the particle centers is that what causes densification. And here it's not densifying. Okay? Well, let's go to the glass case now. Here I have two examples of a nice movie that the glass, these are a bioglass compact, particle compact that is sintering. And you see here the temperature will change during the process. Suddenly it shrinks and densifies, okay? And there you have compact that is sintered. What we see here is that nothing is happening. I'll put it again. Nothing is happening in the beginning of the heating. You just start sintering after TG. When you approach TG, then it sinters. And we see here that this is an disadvantage of this process, is that we trap pores inside the material. And this is another example, just to show you what happened in high temperature. Okay. When is interesting to use sintering? Sintering is nice because, again, we can look for a complex composition and continuously change properties, designing the compositions, look for compositions using machine learning, prospection, and we can look for a lot of compositions that could be sintered. But if you are you're looking to get a glass ceramic, then we increase the possibilities now. Because even for those glasses that are difficult to obtain, you cannot form. You have to quench it very fast. And it's not possible to have a bulk product because it crystallizes too fast, or the viscosity doesn't allow you to form it suitably. Then you can quench, get a powder, and then form using the classical ceramic technology. And what's nicer is that this forming, you can make it at room temperature. You don't need to form at high temperature. If you are not rich enough to have a very big melting furnace and forming from the glass state, you can, in a small facilities, try to get nice glass ceramics for nice applications. You can use some interesting process from the powder technology of ceramics. And you can deal with, instead of a mix of raw materials that is typical from the traditional ceramic process. You can put all this in a single phase that make it easier to process. Disadvantages, you have to deal with porosity. Porosity is very difficult to eliminate, and you have to control sintering before crystallization. Otherwise, you get a powder form, put in the furnace, it crystallizes too fast, and after you have a powder, compact, not a monolith. Okay, you have to control sintering before crystallization. Now let's thinking about how it works. This is a very classical model, Frankel. It's probably the first sintering model, even for crystalline materials. In the beginning, people thought that viscous flow could be approach for crystalline materials, and Frankel was the first to think about that. It's interesting, isn't it? And what we see here is that densification, this is a density, is a function of time, depends on the green density. The green density is the apparent density considering the voids between particles. Actually, no, this is theoretical density, okay? The density of the material. If it achieves full density, you have 100% densification. It depends on surface energy, viscosity, this particle size, and time in a determined temperature. This is a simple model. We are considering here spherical particles in a cubic array, and the particles all have the same size, and this is the first approach for the problem. But actually, it doesn't work all the time. After some time, the porosity closes, and you have individual pores in the bulk, and the geometry is not anymore that Frankel considered. And in this case, we can use the Mackenzie-Shuttleworth model that considers a viscous matrix with spherical pores of same size dispersed in the volume. And in this case, again, you see here, we have the same variables, the initial density. I'm sorry, this is not theoretical density. This is the green density, the initial density, the initial apparent density, surface energy, the pore size, viscosity, and time here. Okay. What we do actually is it's much different from this. Actually, in practice, we have irregular particles, we have a size distribution, and crystallization is happening at the same time. Temperature is changing, and so on. Okay? So how to deal with this? Then Prado, Zanotto, Miller came with a nice idea, is to consider Frankel and Mackenzie-Shuttleworth. Frankel working up to a threshold time, and then Mackenzie-Shuttleworth working after. Frankel just increased density, so it cannot work forever. We have to arbitrarily consider a limit for changing from Frankel to Mackenzie-Shuttleworth, and we have to find the time that happens when this one Frankel achieves. In our case, we considered 0.8 density, relative density, and from this Mackenzie-Shuttleworth is used to calculate the density. Simply, so simple. And this is valid for one particle size. When you have a size distribution, then you have to consider the volume fraction of all the collections of particles in the distribution. And what's nice in this model is that it considers that the small particles are organized in the void of the packing of large particles, and they are all sintering together. So we consider that the particles are more or less spheric, and sintering only together with other particles with the same size. After, there is, I'm sorry, I'm lost to the, I disappeared here, but you have this neck forming ability that bring back the probability of each particle be in contact with other particles with other sizes in the distribution. This is important for broad distributions, but this gives us a chance to calculate the glass sintering without crystallization for a size distribution. And here you see in Zanotto's and Prado work, the model works very well for different temperatures. This is, if I remember, it's soda lime silica glass. And again, we can use shape factor to correct for the variation from spherical shape. But again, something more is happening. I'm going to show you here. We can see here a big particle of a bioglass. There is another particle here. There's a small particle here. They are sintering. Okay, they are sintering. Here you see the temperature is increasing. And what's happening here? We have the DSC of this glass. It's a bioglass with some lithium oxide added. So here is the DSC curve. We have TG, more or less above 500 Celsius degree. Then it crystallizes. This is crystallization peak, about 600. And then you have, after some time, melting of the crystalline phases. Maybe here you have, look into the other curves, maybe you have some melting already here in this region here. And starting again this movie. Pay attention there. The temperature is increasing, nothing is happening. Now we are approaching TG. Now we are in TG. Oops. This is difficult to control. more or less here, we have sintering by viscous flow in the supercooled liquid state. And from now on, nothing much is happening, see? We are already at 800, and from more or less 550 up to 800, nothing else happened because it crystallized. It crystallized here, and crystallization hinders, avoid the glass, the viscous flow, because it solidifies mainly from the surface. And when you crystallize the surface, you cannot anymore sinter by viscous flow. After, then you start sintering again because you are now melting the system, okay? So, all the glasses crystallize on the surface much earlier than it crystallizes by volume or homogeneous nucleation. Some compositions you crystallize first, you nucleate very fast in the book, but they are rare. Normally, you have surface crystallization. And the surface crystallization, you can see some crystals here around the sphere. This is a soda lime silica glass. Inside, it's glassy, or in this case, but in the high temperature during the sintering, it's a supercooled liquid, but you don't have anymore the viscous flow because you have this surface crystallized shell hindering the crystallization, okay? And it can happen very fast, very fast. In some systems, you are not able to crystallize because you have this too fast. You are not able to sinter or densify because surface crystallization is too fast. More or less what's happening here, you have to viscous flow sinter first, and then surface crystallization. This would be the best situation, okay? And we have this kind of microstructure. And how do we deal with this in the clusters model? You see here, now we have Frankel density considering crystallization. Mackenzie, Shuttleworth density considering crystallization. And those are calculated considering the clusters model without crystallization, modulated by the rate of surface crystallization. And the rate of surface crystallization, the surface crystallization kinetics, depends on the surface density of nuclei, crystal growth, and time, okay? Using this model, you're able to observe that now the density in the case of a glass that crystallizes on the surface, it doesn't achieve 100% of densification. You stop before, and because you have crystallization to the right here happening, you don't need to have a large fraction of surface crystallized, but the difference between the saturation density here and 100% is the amount of porosity that you're getting inside your system, okay? And you have to use this model to know what should we do to promote densification and before crystallization. So we have to use glasses with a small amount of surface nuclei or a glass that crystallizes slowly, okay? It teaches us how to organize the system to get the best from the sintering. Well, some nice examples now. Even coarsely crystallized materials can give you some application. In this case, Neoparis is a Japanese glass ceramic produced by sintering. It's used for tiling. What's nice here is you can produce curved surfaces and free of pores. In countries that you have snow, if the water go inside a crack or a pore and it crystallizes there, you have expansion and the material cracks, and year by year you have the cracking of this material and it deteriorates due to the environment. And if you have material that is free of pore, you have a product that's much more strong and resistant to intemperies or to the environment. And I'll skip this. Some difficulties. We have difficult to avoid porosity. You have trap porosity. That's normal in ceramic powder technology. How to deal with this is to control the grain porosity, the grain density. You have to control the particle size distribution to put very small particles inside the space between the large ones, and then if you have a grain density, high grain density, you are in business. This is another kind of pore here. This kind of pore appears when you have a difference, a big difference between the glass density and the crystalline density. You don't have material to, as the crystallization starts from the surface, at some time of the process, you have nucleation of a pore inside each particle due to the density differences. Another problem is to deal with the difference between the thermal expansion coefficient of the residual glass and the crystalline materials. And very often, if you don't control that, you observe cracks in the microstructure. Here is another example of those cracks. It appears mainly in the big particles, and here it's a radial crack that's appearing due to the difference between thermal expansion coefficient of the crystalline phases and the glass. Well, we are always looking for nice properties, but we have to, I'll skip this fast, we have to deal with the problems that we are going to face in the process to be successful to produce a nice glass ceramic. Doesn't matter if a bulk crystallizing glass ceramic or obtained by sintering. Some examples, scaffolds for medical applications. You have to produce that by sintering, by glass sintering the glass powder. These are some materials we obtained in Lamave. For tiles, you have here the material before and after polishing. They have a nice texture and obtained by waste glass from bottles, and in this case, window glass. You see it reflects very nicely the surface here. It looks like some granite or so. These are more recent. We are using mineral wastes from the natural rocks. Brazil is very rich in natural rocks, but they have to destroy a mountain to get just some rocks for surfaces. And we are using the residual, the waste, to produce a sintered glass ceramic. These are our try. What's nice in sintering, my point of view, is that you can use the 3D printing and tape casting, forming procedures to get very, very complex geometries. And then you have to debind, heat it to eliminate the binder, and then finally sinter and crystallize. This is a work made by Ana Caroline. She's here. Probably you have known him here. And, but this is before the binding. After the binding, you destroys it. Another example, very fast, is possibility to use the flash sintering. This is a glass, window glass again. If you sinter together with application of electrical field, and you don't control that, you're gonna see it softening and foaming. But if you are able to control that and stop the treatment in a smart point, you have very fast sintering at temperatures well below the normal sintering temperature. And you're going to see now, it's a little bit red inside. And everything happened. It stopped. That's sintering. And what's nice in this, in the application of this process is here you have the microstructure of a glass powder sintered by the traditional method, and here is using the flash sintering. You see, as the heat comes from inside, you can eliminate porosity. And much more than using the conventional procedure. And here's linear shrinkage as a function of temperature. You have the traditional procedure here without voltage applied. As you increase voltage, you see the temperature of fast densification deviating to low temperatures. Okay, that's it. I would like to tell you. Thank you.
Thank you, Eduardo, for this. Yeah, this is our stopping on time, really on time. So thank you for this nice overview about sintering and glass sintering. This is another topic. This is an important topic also. And we have time for some questions.
Thank you for nice talk. Do sintering has future in optical applications?
Yes. Transparent lenses, even glass maybe. I'm sorry. Hello. I think photonics, yes. But for transparent optics, it's possible, for example, to have a transparent alumina if you control the grain size and you eliminate completely porosity by the sintering from the powder. There are some, but it's difficult. I think you should have a hard work. It's not so easy. Yes, but for photonics, I guess we could find a way. For metasurfaces, we are thinking about this. Metasurfaces. You can build cylinders or some structure for microwave, scattering this controlled surface. That would be nice.
Okay, so, thank you, Professor. Thank you for your nice talk. In fact, I think in your talk you mentioned many times about the porosity in the sintered and glass ceramics. It must be very important because it will have some effect on the mechanical properties like that. So, and also you mentioned the porosity comes from the maybe the irregular shape of the original materials. So my question is it impossible to make the precursor? We use the sphere powder, and to make to center glass, then make to minimize the porosity or even the pore-free glass ceramics like that.
Yes, I don't think it would work because I'm gonna show you. The particle spheroidizes very fast. You see here? You start with a irregular particle, but after some time it gets spheric, more or less rounded. Very fast before sintering and crystallization. The trick here, you see these are big, very big particles. And at that time we are looking for tiles, like granite. And this is difficult to avoid, the porosity inside the powders. One possibility to avoid this kind of porosity is decrease very much the particle size. Then you can avoid this kind of porosity.
Okay.
This is the trick.
I just wanted to comment that for luminescent applications, they are very interesting. We are working on the so-called phosphor in glass composites. So you basically combine a nanometric or micrometric crystalline phase with glasses, and then by viscose sintering you can get at least a composite that is translucid. And if you don't need the transparency, for example, for solid state lighting, you have these panels for lighting, no gas, right? So then scattering is not a problem because you actually want, so no problem. Another thing, Nippon Electric Glass, they also have a composite that is used for lanterna de carro,
car lamp.
Headlights, né?
Right.
Car lights, car headlamps. And again, you know, because normally this was done with polymers. So you would put the luminescent compound in a polymer, make a composite, but then the color deteriorates over time because the polymer degrades. So glasses are much better for that. So it's growing in optical applications.
Yeah. Thank you, Andrea. You're right. This is a nice system to make a composite, a matrix for a composite of functional materials for luminescence and magnetics and so on. There's no end. You can think in that kind of material in a meta surface and so on. We're thinking about this. Roger is here and he's thinking strongly on this in this direction. And the sintered glass is nice because you don't have to heat too much and protect the functional phases without melting inside. Yeah.
Thank you, Edu. Very nice overview. Just to add to your talk, one very effective way to minimize or even eliminate porosity is by hot pressing. Yeah. Now, you sinter under pressure for expensive products, of course. You can use hot pressing, then you can eliminate porosity.
Yeah. Fast heating. We learned it from the models that fast heating can let us lead us farther in the densification before crystallization. That's why we also start thinking about flash sintering to heat it very fast. And of course, pressing and so on. Okay.
I do thanks for the talk. I have a
question, curiosity. You spoke about trapped porosity. Do you know about examples where we have accessible pores in these sinterized materials?
For permeability?
Yeah.
This kind of porosity is not that one, but sure, you can see here. This is the kind of porosity you're thinking about. You have to use a template to copy the porosity of something, like a polymeric foam, for example, and use powder glass to copy the struts, and then you have this kind of very porous material. People from medical applications, they are working hard in this direction. Also for filters and other things.
Hi, Eduardo. Thank you for the nice talk. I was curious. I know we talked about this eons ago, but is there a way to know the temperature by which the flash sintering is happening, especially through that internal temperature?
What we do, I can show you. It's not here, unfortunately, but what we do is to use the model. We write the model for non-isothermal heating, and we have all the properties, viscosity at high temperature, and so on. And it's a function of rate. And then we fit this model to the flash sintering densification data, and we get the rate, and then we have an estimate of temperature. We did that. I'm sorry, just complete that. We did that, and we found the glass compact was sintering at 720. We calculated this for these guys here. So if you calculate it, if you estimate the temperature that was inside the sample, and we found this. We found the softening temperature here, 720. I could show you. Sorry.
May I add some comments?
Sure.
Yes, it can also be calculated by a model which is called black.
Yes, the black body model. We did that.
Body model.
Yes,
so
but
in the recent article from João Vitor Campos, you can find those calculations. It can be calculated by the black.
But it overestimates. I calculated for the black body, and it was above 1,000 using the black body model. And using the clusters model, I calculated this temperature here.
Okay, nice.
It is nice.
Oh, nice. So, any other question?
But it's indirect, unfortunately.
Bom dia, professor. No caso do flash sinter, o senhor trabalha só com flash sintering ou com flash sinter crystallization?
Flash sintering crystallization.
Ok. O senhor acha possível, durante um único processo de flash sinter crystallization, separar a parte da sinterização da cristalização em duas etapas diferentes no mesmo processo? Tipo assim, colocar a amostra no forno, deixar ela por um tempo rodando para sinterizar e depois ajustar novamente as propriedades para cristalizar tudo na mesma etapa?
Don't know. It depends the glass.
He asked if it's possible to separate the sinter from the crystallization during the process of sinter crystallization.
If we would be able to separate first sintering and after crystallization. We have to see the composition, what's happening? It depends strongly the composition. If the nucleation and crystallization is overlapped, it's difficult to avoid.
If the surface crystallizes too fast or not. If the surface crystallizes faster than the viscous flow happen, then the temperature of surface crystallization.
Yeah, that's right. And you gave me another idea.
Yeah.
You have to control surface crystallization. One way is to reduce strongly the surface density of nuclei and washing the surface by some acid or so, you may decrease. There are some works from Hofmiller in Bonn. He demonstrated that you can reduce NS, the surface density of nuclei, by maybe applying some washing, some acid attack, and then it will sinter by viscous flow, and then you let in the furnace for crystallization. And that's the dream. That's
okay. Any other question? No. So let's thank again Eduardo.
Thank you.
And so time, just on time. Yes, that's perfect, Eduardo. Just on time. Yes. So it's time for coffee break, but please be back at 10:15. I know it's short coffee break, but we need this, otherwise our lunch will be...
Sorry, just quickly before the coffee break, we'd like to announce our lucky t-shirt winners from yesterday. If the professors from Alfred could come to the front so we could take a nice photo. Remember that these are the 125th anniversary t-shirts that will only come around once in time. Could you give this to Vinicius to take some photos? Yes. And the two people, there was quite a debate yesterday, but there was a very clear tie that you, sir, come on up, and you, sir, come on up, are the lucky winners for today. Congratulations, you got it. Yeah. Congratulations. We'll do all. Space, guys. Space. Hold the t-shirts up. Oh, you got another t-shirt here. There you go. You guys can go to coffee.
Thank you. I also need to take a picture with you guys.
Yes, please.
Can you borrow?
Bem? Tá bom assim? Joia? Beleza. Deixa eu ver. Tá bom. Tá bem bom. Bom. Aham, boa. Legal. Tá ótimo.
Ah, you came back. Okay.
No, yes. So let's start. It's time to start here. And our next lecture will be about mechanical properties, sorry. It will be taught by Professor Francisco Cervena. He's professor at State University of Ponta Grossa, Brazil, a little bit on the south. 600 kilometers?
500.
500
Yes.
kilometers from here. So Professor Cervena is collaborating with us, with CERTEV since a long time. So it's a very nice, very good also collaborator. Thank you very much, Francisco. And please.
Okay. Thank you for the organizers for the invitation. So we'll talk about mechanical properties of glass ceramics. And a brief outline of my talk will be this. So I hope to finish by 11. And the interest in glass ceramics, the main property which was originally, when it was discovered, was by Stuckey, that he observed that glass ceramics has superior mechanical properties than glass. So in the follow-up, several glass ceramics materials were patented and commercialized. So the driving force for glass ceramics initially was mechanical properties, mechanical strength. So glass ceramics are tougher than glass. So some basic concepts on when we talk about stress and strain. If you get a material and we submit it to a force, if we divide the force by the area, we have stress. And this material under this force, it will deform. So here is a picture. So as it deforms and stretches along the vertical direction, it contracts along the horizontal direction. So if we divide how much it deforms by the initial length, we have strain. And if we divide how much the material contracts as it expands, you have the Poisson's ratio. You can also have two types of strain or stress. You have when the force is applied normal to the surface, you have normal stress, and then when you have the force applied parallel to the surface, you have a shear stress. And you can define a shear strain as how much the material deforms laterally by the initial length. So if you look at the deformation of a stress-strain curve, as you apply a strain, when you apply the stress on a material and you measure the strain, you have this initial portion here for a small deformation that the stress is linear with the strain. So you are under the Hooke's law, and this constant that is gives the proportionality between stress and strain. When the stress is normal, we call elastic modulus, and when you have a shear stress and shear strain, you have shear modulus. Glass is isotropic. Well, in certain cases not, but usually. So, and if you go through elasticity, if you know these two constants, you can derive the others. So if you know, for example, elastic modulus and shear modulus, you can calculate how much would be the Young modulus, Book modulus, and so on. So you only need to know two constants when you have isotropic elasticity. How to measure elastic constants? You can measure under 3 or 4-point bending. So you put some strain gauges to measure deformation, and then you apply a load and you measure stress. You can calculate the stress given the dimensions and the load. You can also measure them by resonance frequency. You just like kick your material, and it has natural vibration modes. It have flexural and torsional. And if you measure these frequencies, you can calculate from these resonance frequencies, the elastic modulus and shear modulus of your sample. Another technique is you produce acoustic wave in your material, like here, and then the sound wave will propagate, hit back in the other surface of the sample return. So essentially, when you measure the time between the travel and you know the distance, so you can calculate also you can also calculate the elastic modulus and shear modulus. This is the longitudinal speed wave, and this is the transversal speed wave. So there is these three ways where you can calculate, measure elastic constants in glass or any material. This is a plot of how the Young modulus of glasses varies against the glass transition temperature. So you see you have here some sulfides that are very low, like 20 gigapascals, and goes up to the oxynitrides about 170, 180. So these are the ranges of the glasses. Glass ceramics stay a little bit higher. And just to show how the elastic constants depends on the structure of the glass, which is Dr. Yoshida talked yesterday. Look here, if you have like a glass with a very open structure, the Young modulus tends to be low. In silica, it's 0.15, 0.16. As you have, for example, for germanium selenides, which has a 2D structure, the Young modulus increase. And as you go, for example, for a 1D structure, which is very compact for a glass, Young modulus is 0.3. And as you go to metallic glass, is even higher. So essentially, the Young modulus measures is related to how open the structure is. And here is a plot as well of the Poisson's ratio with the atomic pack density. So you see that as the packing density increases, the Poisson's ratio increases. Here are some tabulated values of Young modulus for some glass ceramics. And usually the elastic modulus of glass ceramics are higher than the parent glass. Okay? Here we measured how the elastic modulus in glass ceramics measured varied with volume fraction and with a constant crystal size. So as I explained the first day, we are always trying to do clean experiments in order to understand how what we are measuring varies with the microstructure and how much each part of the microstructure contributes to what we are measuring. So here is from, on the left, we have, this is from Oscar Tizes, where he shows that the elastic modulus increases linearly with the crystallized volume fraction. This is one of my PhD students with some other work that shows also that in lithium disilicate, which are both glass ceramics that crystallize in the volume, you can assume that elastic modulus increase linearly with crystallized volume fraction. Other important property is hardness. Hardness is very important for properties such as abrasion, wear, erosion, contact damage, and so on. And also, I'm not talking much about hardness because Professor Yoshida gave a lecture on this. So, but the hardness is a very simple technique. And sometimes this leads to some confusion. But the important thing is, it's very simple from the experimental point of view. But it's not a material property. Okay? So when we talk about hardness, we must specify which indenter, what's the load, what is the rate that we applied. So although the technique is simple, its value depends on test conditions. This is a simple one, which is a Vickers indentation, which has made of diamond, which is the hardest material. And when you press gently on a surface, it leaves a square impression. is this impression here. In glasses or glass ceramics, you have radial cracks. These radial cracks, they are detrimental, but you can use them to measure one property, which means crack resistance, or related to. Another technique that we can use to measure hardness is instrumental indentation. In this case, we have an indenter, and when we press into the material, we measure the load and simultaneously how much or how deep the indenter penetrates. In this case, you have a load by displacement curve of this type, and from this curve, we can measure elastic modulus and hardness. This is just to show several materials, and as you go to the left, you increase hardness, because with the same load, you have a shallower indentation. So this is related to Mohs scale. And as Professor Yoshida told yesterday, when you indent a glass, you have two types of deformation. You have densification, which the material, every time you indent with a blunt indenter, you have this region here under isostatic compression. So the material, if the glass has an unopened structure, like a low Poisson's ratio, it densifies. Or if it has a high Poisson's ratio, you have the deformation by shear. It's important to note that these two mechanisms, they occur at the same time. Okay? So if you go in silica, mostly of the deformation is by densification. If you go to soda lime glass, part of the deformation is densification, part of the deformation is shear. And as you go to other glass structures that are more compact, the more shear contribution you have and the less densification you have. So it's good to keep in mind of these two deformation mechanisms. Why they are important? Because they promote different crack patterns. So here is just to show you the hardness as a function of the glass resistant temperature. So usually the higher the TG, the higher the hardness, and you see oxynitrides, they are almost thicker hardness here, 12, and goes lower up to 2, a very soft material. And if you see here, when you have a low Young modulus, low Poisson's ratio, you have cone cracks. Usually you have a ring crack around here that goes as a cone. This is a cut in the perpendicular to the surface. So you see here the traces of the cone cracks and some median here. So as you increase the Poisson's ratio, you see that you end up with the radial cracks that everybody knows. There is a medium crack behind here. And as you go up, you only have shear deformation. And also, hardness has been predicted using machine learning. So what it tells us in these sharp plots is that if you add network elements, you decrease the hardness, and if you add modifier, you increase. Okay? So this is from work by Manhã 2 years ago. Okay? So machine learning can give you clues on what can play with the chemical composition. Hardness has been measured as well in glass ceramics, and this is varying the crystallized volume fraction, and this is the Vickers hardness. For the biosilicate, you see the hardness increase and then stays at maximum at around 40% and then decrease. And if you go to lithium disilicate, it's another, it's different. It increases linearly. So essentially, that's a problem. We always try to find general rules, but essentially you have to measure to be sure. So each glass ceramic system is each glass ceramic system. Some concept here, theoretical concept. If you have two atoms And this is the force against the distance as you try to separate these atoms. If you assume small deformations and you calculate the stress necessary to separate these two atoms, which you call theoretical cohesive strength, you end up with this equation, which is related to how much the atoms are apart, how much is the elastic modulus. And if you use some common values for example, for a glass, you end up that the theoretical strength to break a glass is about some number, which can vary depending on the model you use, but is a fraction of the Young modulus. So if you have a Young modulus for soda-lime glass of 70 gigapascals, your theoretical strength would be around 10 or 7 to 10 gigapascal, which is very high. But if you go to the real world, you see that this strength is very low. This is the pioneer work by Griffith, which he measured in fibers. So for fibers with diameters of around 100 microns, the real strength is very low. And you only start reaching the theoretical strength as you decrease the fiber diameter. Why is this so? Well, because any surface has cracks, has small defects. So as you apply a remote stress, here the tip of this defect has a stress concentration. So you can break Griffith approach this work in terms of energy. So you have a term belonging to the mechanical energy, and you have a term related to when the crack propagates, it creates surface. So you have a term related to the energy surface. So essentially, when you increase your stress, you increase mechanical energy, and when you have this mechanical energy available to create and propagate unstably a crack, you have the fracture. So if you work out, this stress is related to the gamma, which is this surface energy, elastic modulus, and the size of this defect. So essentially, and then if you put again these values, you can explain the experimental values that we observed. We can also play around with that original equation, and we can isolate it to gamma on the right side, and on this side you have variables including the elastic modulus, the size of the crack, and the stress applied. And we call this energy release rate. This is a material property, or depends also on the conditions like humidity or so on. So when you increase the stress, or when you have a longer crack and your energy release rate is equal to 2 gamma, you have in a condition to fracture. And your GC now is called critical strain energy release rate. So this is based on energy. You can also look at local criteria, which we rearrange that to put the materials property on the right side, and here are variables like crack size and stress, and you call this stress intensity factor. So when this stress intensity factor equals to K1C, you are, which you call critical stress intensity factor, you are at a condition for fracture. So both are interrelated. You can load a crack with different, we call modes, which are related to the direction of the force that you apply. So if you apply the stress like in this opening mode, we call mode 1. If you call in this mode, is mode 2, and this is mode 3 called shear. So for example, if you think of when you cut a paper with a scissor, okay, you essentially are cutting in mode 3. Because your paper is in here, one slide of the scissor is one way and the other goes the other. So usually we have mode 1, which is the most important for fracture, but sometimes depending on microstructure, you may have mode 2 or mode 3. When? For example, when you have a crack propagating and you encounter a precipitate. your crack may tilt or twist. So in this case, also under mode 1, you induce mode 2 loading on your crack front. And here you induce, apart from mode 1, mode 3 as well. And you can relate this when you put additional load moldings to the energy release rate through this equation. Okay? So this is a way of calculating, including these modes here. So if you look at fracture toughness of glasses, you see that glasses are brittle. So you have the chalcogenides around 0.2, and as you increase, borosilicates are between 0.6, 0.8, and the silicon nitride 1.2, 1.4. Okay? So these are low values. Ceramics, alumina, for example, maybe 4, 5, zirconia as well. So glass are brittle. I want to point out that because I told you before, hardness is easy, okay? But when you indent, you end up with those radial crack patterns. And it has been proposed in the literature that from the measurement of the radial cracks, you can calculate the fracture toughness. Well, if you look in the materials or in the literature, you see that there are a lot of reports when people say we have measured the fracture toughness of our glass ceramics, of our material. You go look in there, actually they use indentation. And as a reason, I'll explain you in a bit, we don't call it fracture toughness, we call indentation fracture toughness, okay? It's related to, but it's not indentation fracture toughness. Fracture toughness is important property because it's a material constant. So it doesn't matter which technique you use, you should have the same value. However, when you use indentation fracture toughness, the value that you obtain depends on the technique you use. So there is that model, there is the Nihara model here, which also tries to predict the K1C. And it has been a work by Quinn and Brad, it's very famous. It has almost more than 2,000 citations, where it says that indentation fracture shouldn't be used to measure fracture toughness. It's okay, you measure it and you say, we measure indentation fracture toughness. But don't go there and put in your paper, you have measured fracture toughness. Okay? It's a good indication. Maybe you want to screen among several microstructures you prepare, what are you going to measure fracture toughness really? So that's okay, but I mean, it's important to have this distinction, because depending on the model you have different values, and also they don't fit or they don't approach the value when you measure the ASTM techniques. This is just to show one work that we have done. This is the fracture toughness, and this is the indentation fracture toughness. Okay? Just to mention, glass is subject to fatigue, so when you have fracture, before fracture, if you have moisture, your glass or your crack may propagate at stresses below the critical stress for fracture. So maybe you put your sample in a moisture, and then you are well below the stress for fracture, but then the crack starts to grow and reach the critical length. So your sample breaks. So in fact, your sample broke at a stress level below what you'd expect, just because your defect grew. So this has been, we call this feature fatigue, and you can have, this is a typical curve of a crack velocity against the applied stress. So you have a regime here where below that there is no crack growth. There is a region here which is related to exponent. This is a plateau, and then you have a fixed fracture. Just to show you that these regimes depends on several factors, including glass chemistry. So you see aluminosilicate is more resistant than, for example, soda lime. And when you do fatigue experiments, we try to measure this exponent here. Because the higher the exponent, the higher the fatigue resistance is the glass. Residual stress. When you have a crystal nucleated inside a glass matrix, you crystallize at a high temperature, and then you cool down to room temperature. As you reach Tg, your glass matrix freezes, okay? But then when you continue to cool, your crystal contracts, but also the cavity of the glass contracts as well. But if they have a different thermal expansion, okay, the volume doesn't fit. I mean, or either the crystal will be bigger than the cavity of the glass, or the cavity of the glass would be bigger than the crystal. Anyway, they are bonded, so thermal residual stresses will arise. These thermal residual stresses, it depends on the difference between the thermal expansion between the glass and the crystal, also the difference between Tg and the thermal room temperature, and also on the elastic constants of the precipitate in the glass matrix. The one important thing to notice, the higher the difference in the thermal expansion, the higher will be the residual stress. The higher the Tg, the higher will be the residual stress. Depending on the difference, you may have compression or tension. Also, the residual stress does not depend on crystal size, okay? Does not depend. If you have a nano crystal size, or if you have a 10 micron crystal size, the residual stress will be the same, okay? This is important because people they tend to think larger crystals has higher stress. No, they have larger mechanical energy stored, okay? Yes, that's what I'm going to talk about, okay? And the other thing is that if everything is isotropic, the stress inside your precipitate is homogeneous, so in all the three directions will be the same. But as you go further in the glass matrix, you have the radial component of the stress is the same, so if you have compression here, the radial direction is in compression as well, but the tangential direction flips the sign. So you have tension. So in the matrix, you always have some stress state more complicated than inside the crystal. And also in the case in the volume as a power of cubic power. So it decays very fast. I'm not going to details here. The residual stress is affected by the shape of your precipitates. So if you have a fiber or a rod or a sphere or a disk, it depends on it. So the stress becomes anisotropic. This is just to show a few things that I already talked. You can also have, if you have a thermal expansion isotropy, which is very common when you have a crystal, and this crystal is in a very crystallized volume fraction. The crystal, it contracts and expands in different directions, and it tries to accommodate along these, in the surrounding grains. So you have residual stresses arising from thermal expansion anisotropy. These are some crack patterns that happens in these are spheres, oxide spheres inside the glass matrix. So in this case, you have tensile stress here, and here you have compression. So you see how the crack path is affected by the different thermal residual stress components inside the matrix. Here are some examples. This is a glass grain that was sintered, and then there was surface crystallization. There was a big glass grain, so it fractured. Here is another one. And when you have a grain boundary microcracking, this is none in the glass, in the ceramics. When you do a linear thermal expansion, you have hysteresis due to opening and closing of the cracking. And once you have cracking, if you put a microphone, you detect acoustic waves there. These are some results here. I skip all these slides, which are some experimental results of measuring residual stresses in glass ceramics. We can use X-ray diffraction, NMR, Raman and fluorescence spectroscopy, and also indentation technique. Mechanical strength. Well, the mechanical strength is a property that everybody measures. I don't like it. Why? Because it's not a material property. Mechanical strength depends on the size of your sample. So bigger samples tend to have lower mechanical strength. It depends on the technique you use, okay? And depends on applied load rate. So there are many variables. So also, when you you measure mechanical strength, you should give the experimental details. What was your sample size? What was your jig size? How you polish and prepare the sample. For example, if you prepare your surface better, you have a higher strength. If you prepare let's say, grinding coarse media, you have a lower strength. Okay, so, but usually, remember Griffith's theory, if you have a material with a higher Young modulus, with a higher surface energy, okay, and maybe harder, so it produces smaller cracks, you end up with a higher strength material. So you can measure using 3 and 4-point bending. This is one technique. The other technique is Brazilian strength testing. And I like this, it's a ball and 3 balls test. It has some drawbacks, but it avoids the effect of stress concentrations along the edges. So usually, glass ceramics has higher strength than glasses. And sometimes you observe, I won't have time to go into detail, but this is some nice work done in borosilicate glass, sodium borosilicate glass, so it's spherical aluminum particles. So it varies the size here, and he observed 2 regimes of strength. One where the strength is constant, and the other where the strength increases. So these 2 regimes is essentially that the weaker phase is the glass, so it's in the glass that you have your critical defect. So in this plateau, the spheres in this case are very far apart, so they don't affect the critical defect size. But once you start having them closer, okay, so your distance in the glass between these spheres, they start to be smaller than the critical defect. So in fact, they are constricting your critical defect, and here your critical defect decreases in size. So that's why you increase. So this distance between the particles is we call mean free path. This is another interesting experiment where it uses torial spheres, but it changed the thermal expansion of the glass. Just to see, well, if we have a particle with a higher, lower, or equal thermal expansion of the glass, what will be the effect on the mechanical strength? And they found out that here, G1, G2, these are these data, they are very smaller and smaller, and G3, which are here, they have a higher fracture toughness, they are the same. So the best condition is when you have thermal expansion coefficient equal between the glass and the crystals. But it's not so simple, yeah? For example, if you get lithium disilicate glass ceramics, and you start crystallizing, so you have a glass, you have metasilicate here, and here is strength. You see, you have an increasing strength when you have lithium disilicate crystallization. So essentially, the increasing strength is related to the crystal phase, lithium disilicate. So that's why glass ceramics are not so simple. It's funny, it's interesting, but it's here. You also can, then this is the point that we talked about, Edgar pointed out. Although the stress, the residual stress is the same, it doesn't depend on the crystal size. It has a crystal size to promote spontaneous microcracking. So essentially, the big picture is this. The bigger the crystal, the higher the mechanical energy is stored, and then this mechanical energy is available to create surface by microcracking. So here, just to show some examples of microcracking and its effect on fracture strength, so essentially decreased to 0. Essentially it's this. So you can calculate this critical size, and it works well for simple systems. This is just to show the effect of residual stress on strength. This is a very biosilicate with a constant crystal size from Oscar thesis, a paper. So you see here, this is the residual stress in the glass and the crystal. In this case, it's compressive. But as you increase the crystalline volume fraction, the stress in the crystal decrease, and the stress in the matrix increase. And it's the opposite sign. So if you measure the flexure strength, it increases up to 40%, and then decreases a little bit. Okay? And there is a very small dependence here on crystal size. And if you look for the theoretical models that there are, it doesn't predict this increase. So essentially, in terms of modeling, residual stress does not explain, at least in that thing, the effect on the strength. Here it's just to show you the strength in lithium disilicate as well. So instead of reaching a plateau here, it increases almost linearly. So, fracture toughness. There has been some reports on the literature about which glass ceramics has the higher fracture toughness. So this is an old work, but is the Cerebone, where by crystallizing wollastonite in a circular form, you see that you have an increase of K1C from 0.8 megapascal square root meter up to 2.6. It's okay. It's okay value. It's not very high, but okay. But you have well, it's usable value, and you have a better mechanical strength. So high strength in fracture toughness was attributed to a crystallization of wollastonite. The other glass ceramic that substituted the other one was impressed based on lithium disilicate, which substitutes leucite. If you look here, the flexural strength of leucite is about 112 megapascals, and when you have this microstructure, it increases up to 400. And also K1C jumped from 1.3. Don't believe 3.3. This is 2 something, but even higher than 1.3. Okay? So, and also, you also play a part, a degree of crystallinity. You see 35, double 70. So this material is used now and is much tougher and higher strength than this one. Also, you can find enstatite with a fracture toughness of 4.6, is one of the highest. And this is attributed to the laminar twin with this phase clinoenstatite. And this is just to show you the fracture surface. So you can have this, when you have this clinoenstatite, you have a phase transformation that toughens this glass ceramic. You have also reported indialite, which has a fracture toughness of 4.3, and this is attributed to the crystallization of indialite in carite, and also has a higher, well, not so much higher strength, depends on the technique you use here, but the fracture toughness is high. This is the microstructure, and also potassium fluorate laterite and canacite. This is due to has a fracture toughness of 3.2, and this is a circular interlocking microstructure. And the canacite, they have mica. So essentially when they have interlocking blade structure, fracture toughness around 5, but also when the crack reaches the flake, the flakes it deflects, and also the flakes, they increase the radius, let's say, of the crack. So that's one mechanism why you have this very large 5 megapascals. So far so good, but how can we understand the fracture toughness varies with, let's say, crystallized volume fraction, crystal size, and so on? So it have been studied in 2 ideal model materials, lithium disilicate and barium disilicate. Okay, they are used lithium disilicate in dentistry. Barium disilicate, it has been used for some optical storage media, sealants, as in solid oxide fuel cells and so on. But the oops, what happens? But lithium disilicate, it produces compressive residual stress inside the crystal, and barium disilicate, it has tensile thermal residual stress in the crystal. So it's very good, two good systems to study the effect of residual stress on the properties. So there are some mechanisms where you can increase your toughness. One is based on the residual stress. This model by Taya is very well cited. However, well, the idea is like this. If you have a tensile stress in your crystal, you have a compression, average compression stress on your glass matrix. So this acts as a closure to your crack. So you increase toughness. By the way, if you have compression here, you'd have tensile stress. So you'd have a decrease in the fracture toughness depending on the thermal residual stress. Okay? And if you test them in biosilicate glass, you see that that does not hold. So in fact, you have compression, and you should have a decrease in fracture, but you have an increase. And for lithium disilicate, you have an increase in bending strength, and here K1C increase almost linearly with crystallized volume fraction. This is for a constant crystal size, okay? And then there are other people who have tested other factors. This is Dr. Mariana. She designed LLS2 glass ceramics, but to have different compositions in the residual glass. So the residual glass would have higher, equal, and lower thermal expansion than the crystal, okay? And then the crystal, the microstructure of the crystal would be very close to the commercial dental glass ceramic. So she tested over 50 compositions, almost 200 heat treatments, okay? And she tested also with a different residual glass volume. And in the end, okay, we have measured thermal expansion coefficient, so on, calculated residual stress. And in the end, we couldn't see difference in the fracture strength. Sorry, fracture toughness. So in the sense, fracture toughness wasn't affected by thermal residual stress, at least in the range that we have worked in these systems. We can also quantify crack deflection, because crack deflection is a mechanism for toughening your glass ceramic. So the idea is, the rougher your surface, the crack had to deflect more. So you had to induce more mode 2 and mode 3 loadings. So you have to expend more energy for crack propagation. So the idea is, the rougher your crack surface, the more energy you're going to expend. So this is a profile, a line profile of the fracture surface, just to show the glass is flat, and as you increase the crystallization, it becomes rougher. So I'm not going into details, but you can calculate an angular distribution to this, and then you can, this is the idea when you have a crack tilt and crack twist. So from these experimental distributions, you can quantify the contribution for the increase in toughness, and you see that it does not explain the observed increase. So it may contribute, but it's not enough. The other mechanism is crack bowing. So when the crack propagates, imagine a crack front propagating here. When it reaches the crystal, two crystals here, it becomes spine, and then it has to bow out in order to increase, and then there is a certain radius here where it breaks free from the crystals and then continues to propagate. So this crack bowing is a mechanism. And also if we look here, we cannot explain, at least for the strong obstacles where the crack doesn't penetrate the crystals, it overshoots the prediction, and it only gets reasonable when you have this, which call, this number is related to how, in the breakaway, how much the crack has penetrated the crystals. Also, you can have crack bridging and trapping, so when the crack encounters a crystal, it becomes trapped, so it bows out until it releases, it continues to propagate. But however, it may leave the crystal pining, bridging the two crack surface. So in order to fracture, you need to break the crystal. So again, when you have this experimental here, you see that overshoots a little bit. But all these models, they only work up to 30% of crystallized volume fraction because they are designed for small crystals dispersed in a glass matrix. So they don't work here in this range of high crystallized volume fraction. So it does devise a simple model. Essentially, when the crack propagates, it breaks the surface of the glass, surface of the crystal, and we allowed for a parameter here for some deviation of this. Okay, so it's explained okay. Just to show some mechanisms here, you see a crack propagating. You see through a crystal. Here you have some crack bridging, and the crack stops here in another crystal. Here's the fractured surface. You see here crack bowing here. Okay. Increasing the crystallized volume fraction, you see crack deflection here. You see crack branching. You see crack bridging. Here, a closure of the crack when it cuts a crystal. Here, a very high crystallization. You see that the crack follows more or less where the glass is, where it's subject to tensile stress. You see here another, well, what I observed here, crack deflection, bridging, branching. Okay? So you can construct a board like this. This has been some simulation in 2022, and they observed the same as we observed. It would be nice to get in touch with them and see if they could reproduce the crack roughness that we observed. And some odd work. This is by Dr. Viviane Soares, and she and Edgar designed a new dental glass ceramic based on metasilicate crystals, and it has this house of the cardius structure. And you see the crystals are big, 10 microns or a little bit more. And if you measure the fracture strength and the fracture toughness, you have 3.5, which is very high, and very good fracture strength, which is attributed to this house of cardius structures when we compare to other high-tough glass ceramics. There are some work also on transparent nanoglass ceramics. What happens if you decrease your crystal? Okay. And you see that you have improvement in the strength, but no improvement in this case indentation fracture toughness. Well, I'm going to skip for this one work of my student, PhD. She did study the effect of variation of crystalline volume fraction crystal size on barium disilicate. The message mainly here is that we would expect a simple system as lithium disilicate. It doesn't. Okay. For the first part, although the crystals are very nice with dendrites and so on, okay, they are not a barium disilicate phase. They are metastable case. We have worked with Ben published on that. Also, if you look at the crystallization, you have residual glass inside the spherulites. So in fact, what we measured, you have crystallized volume fraction measured by optical microscope, and when you do X-ray, you get a lower value. So in fact, these spherulites are not as stronger as before. So you have fracture in the microstructure, so you have this decrease in strength. As for smaller radius, you have an increase. These are the micro cracks we are talking about. These are the increase in fracture toughness. You see, it depends on the spherulite size. As you increase this, nothing here is fracture, but as you increase roughly, you have a higher increase in fracture toughness. These are some mechanisms. And just to finish with this slide, if we plotted these two results with glass ceramic with residual stress tensile compression, both observed an increase in fracture toughness. So our conclusion is that residual stress does not have an effect, at least at stress level that we have here, on fracture toughness. Okay? And with that, I just finish with just stating that mechanical properties has a lot of important mechanisms. Thank you very much.
Thank you, Francisco. Thank you for showing us some other results in mechanical properties and this crack bowing. They are very interesting. So we have time for one short question. I'm sorry to... Thank you, Colin.
I'm going to make my question in Portuguese because I don't know how to say some words, so sorry.
We translate, yeah, no problem.
Meu nome é Giovana e eu queria perguntar o que você acha sobre as questões de mimetismo em materiais e se você acha que, sim, quão próximo a gente está de conseguir aplicar essas questões em materiais cerâmicos para a gente ter um aprimoramento nas propriedades mecânicas.
Yeah, she's talking about, asking about mimetism on microstructure, on glass ceramics. I think if you find a way of producing this mimetism, it's a great way. I mean, if you look at it, I have this microphone, yeah. So if you, for example, if you look in the nacre, the concha, it's called the shells. The shells, for example. Now, if you can, it's a very high fracture toughness material. The question is to produce. There are some work by Renan Belli, which he's doing some work with us on Ronnie's thesis. They produce some crystallization orientation in lithium disilicate, and they observe some interesting properties. But I think it's more a way of how can you produce texture in glass ceramics. But if you can, yeah, definitely. Yes, please.
Thank you. Great talk. I'm very curious about the strengthening mechanism, the toughening. Is it still accepted that the cracks weave around the crystalline phases? And if so, why does that linearly increase it to 100% crystallinity? Like, how does the actual ceramic phases make the material so much stronger? What is happening to the crack in the vicinity of the interface?
Yeah, okay, great question. I think the answer is that you have a threshold for the crystal to be continuous, you know. I'm forgetting the name here, but there is a threshold for when you start from one point and reaching the other through the crystals, which is around 30%. So the crack, I think above this crystallized fraction, the crack cannot grow unless it breaks some crystal. And when it starts fracturing crystals, the fracture toughness of the crystal must be added, or you must add to that contribution to the total fracture toughness. So in the end, if you have like a very high crystallized sample, you may have of the total surface area, mostly is crystal and less is glass. So you may do a kind of rule of mixtures in energy, and then you end up with this contribution, mainly contribution of the crystal as you increase your crystallization. You may have an effect of the crystal twist and roughness, but it's not as big as if you have a tougher crystal phase. So I didn't put here, but one mechanism, I think with the main toughening mechanism you can have for a glass ceramic is to nucleate or put a tough phase. So if you have a very crystallized material, then it will make the higher contribution to that. Of course, there is contributions from others, but I think that's the main mechanism.
Okay. We must move on. I'm sorry. Yeah, I think Francisco will be there. I'm sorry, but we must move on. Please, Francisco will be here this afternoon still. Yes, Francisco? Yeah. So we will switch now to a new session. So we will start now the session on electrical properties. And the first speaker is Professor Thomas Pietraszak. He's from Warsaw, from Poland, from University of Warsaw. Is it correct, Thomas?
It's Warsaw University of Technology.
University of Technology. And he will speak with mixed ion, electronic ionic conductor, and also electronic conductors.
So thank you very much for kind introduction. I hope you can hear me well. Yes. And first, let me start with saying that I've been having a great time here with you all this whole weekend. I really appreciate the opportunity to be here and to participate with this wonderful event. So in my talk, I will focus on the electron hopping conductivity, and I will start with some theoretical stuff, I guess, and also I will show you experimental results on giant increase of such electronic conductivity upon nanocrystallization of mostly phosphate glasses. So maybe I will skip the outline and start with short motivation. So our motivation are power sources for portable electronics. As you know, we have more and more portable devices, smartphones, smartwatches, tablets, name it. And of course, to maintain all those devices, we need very good batteries so that your phone can work whole day. Yes, that you can scroll your phone during all lectures at summer school and so on and so on. And therefore, we need better batteries. Also, there is a big demand for electric vehicles, especially in Europe nowadays. So we are encouraged to buy all kinds of electric vehicles or hybrid vehicles. So in hybrid electric vehicles, you can see that you can still have a large tank of gas, and there is also a small battery that allows this hybrid vehicle to drive with electric motor for a while. And then you have plug-in hybrid electric vehicles. As you can see, the tank is usually smaller and the battery is larger. Such vehicle can drive using electric motors for tens of kilometers, so they are designed to get you from home to your work, do the shopping, come back, and plug it for the night and recharge over the night. And there are full electric vehicles. There is no gas. There is only a battery and such vehicles can drive hundreds of kilometers. But the drawback is that the weight of such battery can be several hundred kilograms. And such vehicles are much, much heavier than typical vehicles with combustion engine. Also, public transportation prefers to be green. Here you can see an electric bus in Warsaw passing by our lovely Old Town, and the larger and larger number of buses in Warsaw, in whole Europe, I believe, is becoming electric. So they do not produce any pollution inside your cities. And if you have green electricity from renewable power sources, they do not create any pollution at all. Also, there are some ideas to have electric or hybrid trains, which means that they are not powered from the wires above, but they have own batteries and then can go on electric engine even there is no electricity on tracks. Another use for batteries, especially for sodium-ion batteries, is the green energy. In this plot, you can see an example of energy demand through the whole day, from midnight to another midnight, and two curves: solar output, which is high, obviously during the day, and wind output, which is quite random, depends on whether it is windy or not. So obviously you can see that those three curves do not fit together. Yes, the production of green energy does not fit really demand. So either we need to still have traditional power plants to fill the gap, or we can couple them with a huge battery facilities. And as you can see in this plot up here, when you have low load from the environment, from the cities, right? But high production of energy, you can charge your batteries, you can charge your energy storages. And when you have high load, which is higher than the instantaneous production of energy, you can discharge the batteries. And in such case, let's say, hybrid power plant can produce all the energy we need, regardless the actual production from wind or from photovoltaics. Okay, so that was a kind of motivation for this topic, but now let's move to the thing we all like, so physics, right? So what theory stands behind electronic conductivity in oxide glasses? And I will focus on oxide glasses containing transition metal ions, so like vanadium, iron, manganese, and some others. So the conductivity in such glasses was given by Mott in 1960s, and it is called the theory of polaron hopping. So firstly, let's start with understanding what actually the polaron is. In such glasses, as I said, we have transition metal oxides, and what is funny with transition metals is that they have partially filled 3D orbitals, and they like to be at different oxidation states. So usually in iron glasses, you will find both iron 2+ and iron 3+. In vanadates glasses, you will find vanadium 4+, vanadium 5+ aliovalent ions. And when we talk about, let's say, iron 2+, it's actually iron 3+ with one additional localized electron. This is one localized 3D electron. And when such electron appears at the ion, it interacts with the surrounding ions. This interaction causes deformation of local neighborhood of this ion, and this deformation causes or produces a potential well for the electron. So we have a localized electron, we have local deformation of ions, which produce the potential well in which the electron is trapped. Therefore, we call this mechanism self-trapping, because it's electron who actually made this trap for himself. And this whole thing, so electron and the potential well and the whole deformation around, is called a polaron. So when the electron jumps, it somehow takes this deformation with itself. So this is why we will call the polaron jumps between aliovalent ions. Another important parameter that we will use will be this WD. This will be the measure of disorder in glass. You know that in glasses, we do not have a periodicity, so each aliovalent ion has slightly different energy, right? So jumping between two sites needs some energy that will be, that is stated here. Like this, the beginning and the final state do not have the same energy. And there are two main mechanisms of hopping that I will show you. The first one is shown here as the red arrow, let's say the A mechanism. So as you can see, the hop is to the nearest neighbor, regardless the difference of energy. The second mechanism, the B1, as you can see, it's not the closest neighbor, but what is characteristic in this jump is the lowest difference in energy, right? So let's keep this in mind, and we can take a closer look into those two mechanisms. So first one is called phonon-assisted hopping, the A one. And there are plenty of formulas, but actually when we go one by one through them, I think you will see that it's pretty reasonable. So now we want to derive the formula for electronic conductivity. So the electrical conductivity is given by, sigma is given by this formula. It's mobility times the electronic charge and times the density. And we can approximate the density, the carrier concentration, because it is the number of carriers over the volume, so it is proportional to the R to the power of -3. The R will denote the distance between the nearest neighbors, the nearest hopping centers. Then we have diffusion coefficient. Here is the mobility, so we can actually calculate the mobility from this formula. And there is the diffusion coefficient that we can approximately say that it is square of the distance over the characteristic time of jumps. So the distance of jumps over the time of jumps, and times, very important, the probability of successful jump. So not every attempt of jumping will be successful. 1 over tau is the frequency nu, and here the probability splits into two elements. So before we get to the probability, we can say that the frequency of this electron attempts to jump will be a function of time. So, sorry, the function of temperature, obviously. So the higher temperature, the higher frequency of those attempts. Now, the two probabilities are extremely important. First one is here, given by this simple formula. Now, let's look what's the C. C is the fraction of, let's say, starting hopping centers. So if we have hopping vanadium 4+ to vanadium 5+, the C will be the ratio between the vanadium 4+ and all atoms, all atoms of vanadium, of course. 1 over C is the fraction of, let's say, final hopping centers. So if we multiply these two, the fraction of starting hopping center and the fraction of final hopping center, we will have, let's say, the statistical probability that the hopping may occur. The second term is tunneling probability. You know that electrons are quantum particles and they are pretty lazy. So instead of going all the way up over the potential barrier and ending up here, they prefer to tunnel, right? If you have a nice potential barrier, it's what electrons do, they tunnel. So this term, which you can see, is a probability of tunneling through this barrier, and it depends also on the distance. The longer the distance is, the lower probability of tunneling. So now we can get all these guys all together, so coming from this side up to this formula, and eventually we end up with this equation. So after all this explanation, I hope that this formula doesn't look so scary as at the beginning. Now we should understand what are the reasons for this formula. And once again, because this is extremely important for the rest of the presentation, the key factors for electronic conductivity here will be those concentration rates, and as you know, the relative concentration, right? So as you can probably easily see, the maximum of this function is for C equal to 1/2, right? So the perfect situation is that we have half ions of V4 plus, let's say, half ions V5 plus. And another key parameter is R, the distance between the hopping centers. It appears in several ways, but in each place, it makes the same job. The smaller distance, the bigger conductivity. I didn't talk about activation energy. So the activation energy depends approximately on two terms. First term, we already know. It's the measure of disorder in our glass. Second term is the hopping energy. And basically, it is the distance that has to be, sorry, not the distance, this is the energy that electrons should have to successfully tunnel from one quantum well to the other well. And obviously, if the wells are overlapping, the energy will be lower, right? Because the barrier will be lower and the tunneling will be therefore easier. So assuming that most of those quantities are independent of temperature, we end up with really nice formula, and you will probably know that this is so-called Arrhenius formula, which is quite popular, really popular dependence on temperature. We will use it later. Now maybe a little shorter explanation of variable range hopping. So the second mechanism I mentioned. In this mechanism, electron prefers to make a longer jump, but with smaller energy difference. Maybe one thing I didn't mention in the previous slide, this phonon-assisted hopping mechanism is observed for relatively high temperatures, so above 1/2 of Debye temperatures, which for many glasses actually means room temperature and higher. So this is the dominating mechanism at room temperatures. Also, those phonons are not to be negligible here, because in this mechanism, it's optical phonons that play a role. And we know that in optical mode, the atoms will do motion like this. So they will have vibration in the opposite phase. And this is also, and at the moment that they are closer to each other, that's an excellent moment to jump, right? if you have two jumping balls, the perfect moment to jump between them is when they are the closest, right? So that's why optical phonons are important in this approach. But when the temperature is lower, usually it is said that it is approximately 1/4 of Debye temperature, there are not so many optical phonons that can assist in that hopping. So electron has lower energy and will try to jump for longer distance, but using lower energy. And this is what the derivation of this model is based on. So we assume at the beginning that in the sphere of radius r, so that's the distance between two hopping centers, there can be only one electron state. I mean about the hopping electrons, obviously. So we have an energy needed to jump and the density of states. From here, we can calculate this activation energy depending on the hopping distance. And we use the same probability as previously, so tunneling probability and temperature-dependent, let's say, frequency probability. And we take this formula and try to find the maximum of this value. So we try to find the distance r at which this probability will be the highest. So after some relatively simple but boring calculations, we can find this r max. So it is the distance at which the probability will be the highest in this case. We use the same formula as previously, but use this r, and we end up with this expression. Pretty similar to Arrhenius' formula, but take a closer look what's going on here. We have t to the power of 1/4. So that's a huge difference between Arrhenius' formula. And this t to the power 1/4 will be a kind of a fingerprint of variable range hopping. When we see such dependence, we may say, oh, that's variable range hopping. Cool, right? This is a kind of a method that you can actually try to calculate or estimate from your experiments the density of states at Fermi level, because this is somewhere hidden in those formulas. So these were the two main models of electron hopping in oxide glasses, but there are also a few other, maybe less popular theories. I want to mention about two of them very briefly. First one is the Schnackenberg theory. So this theory tries to describe the electronic hopping in between the phonon-assisted hopping and variable hopping, somewhere between 1/2 of Debye temperature and 1/4 of Debye temperature. And what Schnackenberg says is that when optical phonons are frozen, we will have decrease of activation energy, and more acoustic phonons would participate in hopping. So after some derivation, he proposed such formula, which is quite similar to Arrhenius' one, but in his approach, the activation energy is not a fixed value, but it is given by this formula, which doesn't look very nice, right? But here is an example from Piotrek Okoczuk. He's from Gdańsk University of Technology, north coast of Poland. And this is vanadate telluride glasses. And as you can see, he used this Schnackenberg formula to fit his experimental data from 400K to about 150 kelvins. And you can see that the fitting is really, really nice, right? The drawback of this theory is that it is multi-parameter model. So unless you are a geek, it may be somehow challenging to fit it well, and it may consume some time. So I haven't seen people doing this frequently, but you can get a pretty nice result. Another approach proposed in Supirolli paper a while ago is a kind of multi-phonon hopping. So this formula actually is a product of phonon-assisted hopping, the Arrhenius formula, and variable range hopping. So it doesn't bring any new physics, I would say. But with this formula, you can try to fit your data in a wide temperature range. This is something I did around my PhD studies. Vanadates glasses from about 200 Celsius this time down to liquid nitrogen temperature. And as you can see, it was possible to fit this formula quite reasonably to the whole range of data. So it looks nice. However, the fitting parameters may have unphysical values. And by unphysical values, I mean, for example, the activation energy, which was 0.03. In this case, it was around 1 order of magnitude lower that comes from original fitting of Arrhenius formula. So it's nice fit, but there is no big physics behind, I guess. But it looks nice. Yes, it's still better than 30 orders of magnitude, right. So another and the last slide in theoretical part, something quite interesting, magnetic polaron hopping. So we are now experts of normal, let's say, polaron hopping, right? But there is also some kind of magnetic polaron hopping which appears in iron glasses. Here is an example of lithium iron phosphide. This paper actually is about crystalline materials, but we can apply this to glasses as well. And what's interesting in case of iron is its electronic configuration. So as you know, when we have 3D orbitals in free ion, in isolated ion, we have degeneration of energy. So all 5 3D orbitals have the same energy. But when our ion is surrounded by other ion, we observe the splitting, depending on the neighborhood, the coordination number. So for a tetrahedral field or tetrahedral coordination, we will have 3 orbitals at higher energy, 2 orbitals at lower energy. In octahedral field, which is the case in lithium iron phosphide, we have 3 orbitals at slightly lower energy, 2 orbitals at higher energy. So now let's take a closer look at configuration of iron 3+. There are 5 electrons in 3D orbitals, and according to, well, starting from the beginning, first 3 electrons will obviously occupy the lowest 3 orbitals. Now, there comes 2 other electrons, but according to Hund rule, they will go to the upper levels because they want to be paired with the lower electrons. They are quite unsociable, as you know. This is what the Hund rule is about. But then comes the 6th electron. So we make iron 2+, the 6th electron makes iron 3+, iron 2+, and now the only way for this electron to appear is to have the opposite spin, because now this guy has to make a pair with one of this one. So it has to have the opposite spin. Okay? And now he would like to jump. So he would like to make a hop to other iron ion. And because its spin is down and it has to pair with other electron here, so the only possibility to find the hopping iron is to find an iron with the same electronic configuration. It cannot be down spin configuration, it has to be up spin configuration. So this is why they call it magnetic polaron, because it can only jump between two alliovalent iron ions who have the same, let's say, magnetization, yes, the same total spin. So therefore, such hopping will be possible only when we have magnetic ordering in our material. That's kind of interesting situation. Okay, good physics is not bad, but better move to some experimental stuff now. So firstly, let me introduce a little bit the idea of thermal nanocrystallization. Firstly, in the way we do it in our laboratories. So just to show you a picture of batteries, you will probably know that such batteries contain of a cathode material, cathode electrode, anode, so negative electrode, and the electrolyte in between. The electrolyte should be only ionic conductor so that we do not have a short circuit inside, but the cathode has to be mixed conductor. And in this slide, I show you some crystalline cathode materials for lithium and sodium-ion batteries. I missed the obvious one, lithium cobalt oxide, because I'm not interested in this one. Here you can see vanadates and phosphates. So for example, we have lithium vanadate, where lithium ions can flow in the layer between the vanadium pyramids. We have lithium iron phosphate olivines when we have tunneling transport of lithium ions. We have a broad family of nasicon-like materials. I call it nasicon-like because originally nasicons were ionic conductors. I'm pretty sure we will hear about them in the next presentations. This one has vanadium instead of zirconium, and this vanadium introduces electronic conductivity, making it the mixed conductor. And quite recently popular alloy-like cathode materials, slightly similar composition, but as you can see here, we have 3 transition metals rather than 2. Okay, so when we look at the composition of such materials, the nominal compositions here, we can rewrite this in oxide glass systems, because it was not an accident I showed it to you, right? They contained a lot of phosphates group, vanadium oxides, iron oxides, and so on and so on. These are all either glass formers or glass modifiers. So what we do when we see such composition? Well, obviously, we make a glass, right? This is what we do. So in this approach, we prepare amorphous analogs of crystalline cathode materials. Then we apply a proper thermal treatment, and we end up with nanomaterials with hopefully improved parameters. Obviously, I will focus on electronic conductivity in my talk. And why this works? So what we think is that when we have nanocrystallites, they have pretty well-defined core, for example, V2O5 core, surrounded by a highly disordered shell. And obviously, everything is surrounded by a residual glassy matrix. So in this shell, we can have high concentration of alliovalent ions, which creates an excellent hopping centers for conductivity. Syntheses are relatively simple, so we mix reagents. Quite often, we use a double crucible technique to provide a reducing atmosphere, so our batch is inside the inner crucible. and in the outer crucible there is some form of a coal, where you burn the coal in lack of oxygen, you produce carbon monoxide, and this carbon monoxide can reduce your transition metal oxides inside your batch. Then we melt it and do the quenching. This is quite trivial. So now, several experimental examples on giant increase of the electronic conductivity. So I will show you several Arrhenius plots. In the y-axis, we have a logarithm of conductivity times the temperature. In the x-axis, we have 1,000 over the temperature. So the right edge is the cool one, the left one is the hot one. And we measure the conductivity of our materials during their heat treatment. So as you can see, we started from a poorly conductive vanadate phosphate glass. We go all the way up according to Arrhenius formula. Then at crystallization peak, we observe an irreversible increase of the conductivity, and we heat a little bit further, and then we cool down. As you can see, we observe an irreversible increase in the conductivity. These were 3 orders of magnitude, and significant decrease in the activation energy. And always, when we observe such a situation, we see the really nice microstructure of our samples. Here is 100 nanometers. So you can see that this highly conductive material is composed of nanocrystallites with 20 or 30 nanometers in size, being in pretty good contact with each other. Here we can see the same material, but measured in much wider temperature range. So as you now, let's say the positive temperatures are here in the left part, and the purple data points were measured in liquid nitrogen cryostat. So as you can see, at lower temperatures, we observe systematic deviation from Arrhenius formula, right? The straight lines are the Arrhenius formulas and the Arrhenius fits for phonon-assisted hoppings, and at lower temperatures, we observe derivation for both glass and nanocrystalline materials. But when we plot it as a function of t to the power of minus 1/4, the linear plot, the linear fit at lower temperatures is really, really nice. So this is the fingerprint of variable range hopping in those materials. That's another picture I like to show. This is a high-resolution TEM image of lithium iron phosphate glass. This is not as beautiful as the one we saw several days ago, but this is the bulk glass. This is just a sample of bulk glass that was prepared for imaging in TEM. And what I wanted to show you is that indeed the local order in glass really resembles the local order in crystalline materials. This is the local order in lithium iron phosphate, and we can see here iron 06 octahedron surrounded by PO4 tetrahedra. And if we have a little bit of imagine, we can probably see that there are brighter and a little bit darker features in this STEM image, presumably octahedra and tetrahedra connected with each other, creating a random network. Lithium iron phosphate was a material that in which we observed a really huge increase of the conductivity, partially because its initial conductivity was extremely poor, 10 to minus 11 Siemens per centimeter. And here we try to optimize its conductivity. First way was to play with the maximum heat treatment temperature. So each cooling branch comes from different maximum temperature. And you can see that In this case, it was 460 degrees, slightly above the crystallization temperature, as you can see here in DTA. Also, we played with vanadium. We used several different compositions with different vanadium content. And in other paper that I do not show here, we proved that it's mostly vanadium that is responsible for conductivity. However, if you look in this plot, you will see that actually the best performance, this is the best curve that we obtained for each composition, the best performance was for the lowest vanadium content. So what's the key factor in here? It occurred that the highest conductivity was observed in the situation when we had really, really small nanocrystallites. So here, the scale is 5 nanometers. And you can see that in this material, the red one, the crystallites were really, really small, like 5 nanometers. They had huge share of crystallite shells. And those shells are believed to provide such excellent conditions for conductivity. In the materials we had more vanadium, the microstructure was not so favorable. The grains were bigger, there were less content of shell, and the shells and the final conductivity was even lower. This is several images showing you this is how we initially imagined our nanocrystallites. This is how we actually observed them. So you can see the well-defined core, nice crystalline layers, and then there is this thin layer, the shell, right? So the interface between the core and the residual glassy matrix. Here is, we believe that the conductivity, or the most on the conductivity, takes place. Of course, such huge increase in conductivity was a little bit suspicious, right? So there were several hypotheses that this was not nanocrystallization. 2 decades ago, there was a paper with quite similar plot for crystalline materials, lithium iron phosphate. These guys dope it with very little amount of niobium, I think aluminum, something like this. It was around 1%. And they showed a huge increase of the conductivity. So a little bit similar to our results. However, and later it was proved that it were metallic impurities in their case. But their Arrhenius plot show nearly constant temperature dependence of the conductivity, so rather characteristic for metals, whereas in our case, it was an Arrhenius-like behavior with reasonable activation energy for electronic hopping. Also, we didn't observe any phase impurities, which later they did. Some people said that, oh, you have vanadium, it may be metal to isolator transition in vanadium 4+. Yeah, that happened. But to discard this hypothesis, we produced a glass with vanadium VO2 precipitates made on purpose. And you can see how metal to isolator transition occurs. At about 67 degrees, both on heating and cooling, we observe a reversible step in the conductivity. Yes. So this is how metal to insulator transition in VO2 looks like. Our effect was irreversible, right? We did some tests in lithium-ion batteries. This is not our priority, but we want to know if it works. And it somehow worked, yes. For those of you who know lithium iron phosphate, its theoretical gravimetric capacity is around 170 milliamp hours per gram. So our performance was around 100. It's not outstanding result, but what I want to show you is that this cathode material work pretty well at high currents. So for those of you who are not familiar with this, this C means a current that would charge or discharge your cell with the theoretical capacity within an hour. So the current 3C means that you discharge your battery in 20 minutes. So it is relatively high current. And this fate is the typical behavior in our cathode materials, in our batteries. Our materials did really, really well even at high currents. So still significant number of capacity remained. At slightly more complicated composition, we added also some manganese instead of iron. We charge our batteries at very low rate to observe the features of the charging curve. And normally, lithium iron phosphate is two-phase, or there is a two-phase mechanism. So all the way around between charge and discharge, you will have two separate phases. The one with lithium, the second one without lithium. In such mechanism, when you look at the charge-discharge curve, and this one can be observed here, but unfortunately, this is a very nice curve, but the plot is twisted 90 degrees. So you have to turn your head right, pi/2 angle, and then you can compare our plot and this plot. So for normal crystalline material, you observe this plateau. So very high range of charge-discharge. The potential, the voltage will be the same. And they synthesize lithium iron phosphate nanoparticles, 40 nanometers, and they show that it's such small particles you probably can observe a one-phase mechanism, and its fingerprint is this blue edges, so the red curve. Instead of having white plateau, you have more monotonic change in the discharge or charge curve. They also observed with XRD that there was a constant monotonic change in unit cell parameters, also proving the one-phase mechanism. And this is probably what we also observe in our case. Here we had two redox pairs, so iron and manganese, but at two potentials, as you can see, we do not have a very distinct plateau, but we have more smooth charge curve. So this is also the clue that in our nanocrystallites embedded in glassy matrix, we probably observe this one-phase mechanism of charging, discharging in lithium iron phosphate. This was also probably the answer, where is the missing capacity? Well, probably the missing capacity related to vanadium is above the stability window of electrolyte. So we couldn't go further with the voltage because the electrolyte would become unstable. Here at very low current, we managed to charge about 80% of theoretical capacity. But as I said, at pretty low current. So I'm pretty good with time. So just final remarks. What I wanted to show you is that the growing number of glassy analogs of cathode materials studied by us can undergo thermal nanocrystallization. And I didn't show you many of materials that my students recently synthesized, but we tried this with nacicon-like, we tried this with aludites, and the results were pretty much similar. We showed that we can increase the electronic conductivity up to around millisiemens per centimeter at room temperature, and always the microstructure with small nanocrystallites and the amount of transition metal are crucial factors affecting the electronic conductivity. And we discussed it based on the core shell concept and Mott's theory of electron hopping. So I think I can stop here.
Thank you.
So thank you for this clear and interesting talk indeed. I think it's a very nice subject, and I believe you have open question on those materials. So, but the results are really impressive. I have a similar result where is Rone, is not here, with Chico. This reminds us our last paper, which we supposed to have a core with high ionic conductivity, but let's talk after. So, is there any question? Yes, Shweta.
Thank you for the nice talk, Professor. So I just want to ask about, you showed one graph about the vanadium phosphate glasses, and you showed that the Arrhenius curve, it's changing at the crystallization peak, right?
Once again, sorry?
The Arrhenius curve, the slope is changing at the crystallization peak. That's what you showed.
Yes. Let me go back, right?
Yeah. Yes. So I wanted to understand what is the mechanism which is happening because of which at the crystallization peak we see the change of the slope. Because in glasses, if we know, and if we talk about ionic conductivity, basically glass transition temperature would be the range. So below glass transition temperature, we would be seeing a particular kind of relaxation or motion, and as the sample changes from glass to, again, crystal, the dynamics changes. So why is it happening at the crystallization peak? I want to understand.
Okay, this is a really good question. Firstly, please remember that this is electronic conductivity only, so it may be and probably is slightly different in ionic conductivity, right? So here the relaxation seems not to have much influence on electronic conductivity. This is what we observe. We also try to perform these measurements at the same heating rate. As you know, in DST or DTA, when you change the heating rate, the observed glass transition temperature and crystallization shifts. So in this plot and all the plots I showed to you, the DSC curve is measured at 1 degree per minute. And this is also approximately the same heating rate during the electronic measurements. So that's the case. Also, the thermocouple from which we read the temperature is situated next to the sample. So this is not the temperature of the furnace. This is more or less the temperature of the sample. And yes, indeed. Well, if you talk about relaxation, it's maybe not clearly visible, but there is in this region slight deviation from Arrhenius formula. When I was younger, I tried to fit VTF formula to this one, and it worked somehow nice. So relaxation, yes, indeed, it may be here, but this is very small effect. Only when the nanocrystallites appear during the crystallization, we have this significant increase in the conductivity. And when they grow a little bit more, I believe that their contacts are better and better. So even though they are slightly bigger, the interaction or the conduction path between the grains become better. So this is why most of the time we reach the best conductivity not somewhere here, because here we would have the small nanocrystallite, right? If we interrupt the crystallization process somewhere here, we would have small nanocrystallites, but we want them to grow a little bit so that they are in good contact between them, right? So your question was about relaxation. The relaxation can be visible, believe it or not, somewhere here.
Yes, and apart from that, I wanted to understand, like in terms of what is the mechanism of electron hopping or motion which is occurring at crystallization temperature, because of which there is a huge deviation in the conductivity values.
But do you mean what is the difference between different samples, or why it's bigger in nanocrystalline materials, or both? Hmm? Okay, so when we go back, well, I must say that still we didn't make a good qualitative analysis of this. It is still quantitative, and in the near future, I wish to elaborate on this, so to get really good quantitative explanation. So at that time, I cannot give you the numbers. But what I can tell qualitatively, right, that in nanocrystallites, you will have smaller distance between the hopping centers. You will have better ratio between, let's say, vanadium 4 plus, vanadium 5 plus. And yes, so these two factors that you can take from geometry, let's say, right, or you can somehow estimate, and we shall do this in the future, leads to the increase of this factor, right, C times C minus 1, it becomes bigger. Also the R parameter, when it's growing, right, when it's smaller, so it is here, here, and it is also in the activation energy hidden here. So the smaller R will increase this fraction, right, will increase this exponent, and will, it's maybe not extremely obvious, but it will decrease the activation energy.
Okay.
Being one not so familiar with this material, you showed this lovely conduction pathway that seemed to be on the edge of the crystal with the residual glass. And I'm trying to think of, in terms of engineering and modeling, are we worried about these processes in the crystal, in the glass, or is there something different about that interfacial area that is allowing this to happen? Could you comment on how to understand that better?
I think it depends on who's asking. Because if you want to have a good battery, I guess we should have as little residual glassy matrix as possible, right? But on the other hand, when we go further with crystallization, so to get rid of the glassy matrix, we will have larger grains. We have larger grains, I guess, so we will have lower electronic conductivity. Maybe I can show you one example. I didn't have time to show it in the main presentation, but this is an impedance figure of mixed electronic ionic conductor after nanocrystallization. And firstly, I will make it a little bit larger. So firstly, we conducted this measurement in typical range up to, let's say, 10 megahertz, and we observed 3 different processes. So we could tentatively ascribe this to ionic conductivity of whatever, actually, electronic conductivity of shells, probably, and shells, grain boundaries, and interior, and that looked pretty complex. But then we sent our sample to our colleagues at Vilnius University. They can measure impedance up to 10 gigahertz. And in this gigahertz region, they found another semicircle. So when you combine those results, now you have at least 4 processes that you observe. And then poor authors need to somehow assign electrical processes to these figures. So we proposed a pretty simple equivalent circuit with 4 RC elements, but obviously there can be, I think, 6 processes that you could ascribe those 4 elements, because you can have ionic conductivity in the glass, in the residual glass, the grain boundaries, grain interior, and then electronic conductivity of residual glass, shells, and inside grains. Yeah? And it's obviously, we cannot with any certainty says which process can be ascribed to these 4 elements, right? It's always a kind of a educated guess, let's say.
Okay, but this is, you refer to ionic conductivity in the lithium phosphorus iron glass, not vanadium phosphorus.
No, this was actually Nasicon-like, but by mixed conductor with vanadium. But this is mixed conductor.
Thank you, Thomas. Nice presentation. Just one observation and a fair question. Could you return to your slide 12, please?
Which one?
12. Yeah. Just as an observation, I guess that the pre-exponential factor in log scale is 12, right? And your activation energy is very low, 0.03. Is my guess. If you decrease the log, the pre-exponential factor for lower values as 3, as the limit of your conductivity at high temperatures, perhaps you should get a higher energy, activation energy, much higher. It's an observation. And the second one is about the slide 21, about your figure. You show a crystallized sample, right? Do you have an idea of the crystallized fraction?
That's a difficult question. So the answer is no. The only we can estimate from SEM images. Yes, no, not here, but obviously we have. At XRD, we didn't observe any residual halo, or very tiny at least. So this is another thing we need to take a closer look. And I'm very, very, very happy to give you this talk, because I hope you may have some additional comments and we can discuss on some issues related to this topic and maybe initiate collaboration, because I'm aware of the fact that we are missing several, let's say, approaches or several things that has to be done, especially in quantitative way.
Okay, thanks. Really nice presentation, especially concerning the motivation of smart grids. My question is fairly simple and is related to detail of experimental procedure. When you show the reducing atmosphere, yeah, can you show the picture again? I was just like trying to understand better. So let's say you have like a bigger crucible where you put coal inside, and then you have the crucible where you put the melt, and then do you seal this to put inside the furnace, or like the bigger crucible with the coal inside, it's like open in the furnace atmosphere?
So initially we used chamber furnaces. So it was that the second crucible was covered with a lid and put inside the furnace with simple atmospheric atmosphere, right? Now, usually for this synthesis, we use an inductive furnace. So the outer crucible, that one, is actually made of carbon, graphite, and there is no, let's say, other furnace, right? The outer crucible is the heating chamber, let's say.
Okay, so you have like a carbon and then an inductor.
So outside this outer crucible is the inductive coil and the whole world around. You know, there is no external chamber. This is kept in air. And we played a lot with this reducing atmosphere, depending on the temperature, time, also the way that you cover your lid. You can do really, really different tricks. I showed on Monday that we managed to reduce European ions from 3+ to 2+ using this method. And this was easily observed by photoluminescence. So it works. It's quite simple, I guess. Maybe not very reproducible sometimes. My students are mad about this because you sometimes change something, you change a day of the week and the results are slightly different. But when you are lucky, it really works.
Okay, and do you see like any leakage of smoke out of the outer?
Well, usually,
I mean, like CO2
usually
and
not the
CO2.
smoke is the biggest problem. Quite often it can be ammonia from
reagents.
From reagents, yes. So smoke, not really. Probably what we could see would be carbon monoxide. But if we smell too much of this,
Yeah.
I wouldn't tell you now. I wouldn't be here, right?
So, thank you. We have time for one short question. Is it platinum crucible?
Initially, we used porcelain crucibles, but now we try to use platinum crucibles. However, in such conditions, the time of life is not very high.
That was my question. Yes, because platinum and carbon will be destroyed.
I have some questions, but I will talk to you personally. So we have, is there any question, more a short question? No. So this is very nice discussion, but we must be back here 1:45, okay? So little bit rushing, because I have a talk, Caio Bragato will have a talk, then mine. Then the Corning lectures will be by some researchers from Corning, and they have scheduled, so we cannot delay a little bit because they are waiting in the United States. They have a right time. So please be back 1:45, okay? And have a good lunch to all, and let's back.